Trace amounts of hydrocarbons, thought to be produced via hydrolysis. Neptune is the 8th planet from the Sun and the farthest IAU-recognized planet in the Solar System. It is the 4th largest planet in the Solar System by diameter, the 3rd most massive planet, and the densest giant planet. It is 17 times the mass of Earth, and slightly more massive than its near-twin Uranus. Neptune is denser and physically smaller than Uranus because its greater mass causes more gravitational compression of its atmosphere. Being composed primarily of gases and liquids, it has no well-defined solid surface. The planet orbits the Sun once every 164.8 years at an average distance of 30.1 astronomical units, 4.5 billion kilometers, 2.8 billion miles. It is named after the Roman god of the sea and has the astronomical symbol, representing Neptune's trident. Neptune is not visible to the unaided eye and is the only planet in the Solar System found by mathematical predictions rather than by empirical observation. Unexpected changes in the orbit of Uranus led Alexis Bouvard to hypothesis that its orbit was subject to gravitational perturbation by an unknown planet. After Bouvard's death, the position of Neptune was predicted from his observations, independently, by John Couch Adams and Urbain Le Verrier. Neptune was subsequently observed with a telescope on September 23, 1846 by Johann Galle within a degree of the position predicted by Le Verrier. Its largest moon, Triton, was discovered shortly thereafter, though none of the planet's remaining 14 known moons were located telescopically until the 20th century. The planet's distance from Earth gives it a very small apparent size, making it challenging to study with Earth-based telescopes. Neptune was visited by Voyager 2, when it flew by the planet on August 25, 1989. Voyager 2 remains the only spacecraft to have visited Neptune. The advent of the Hubble Space Telescope and large ground-based telescopes with adaptive optics has recently allowed for additional detailed observations from afar. Like the gas giants, Jupiter and Saturn, Neptune's atmosphere is composed primarily of hydrogen and helium, along with traces of hydrocarbons and possibly nitrogen, but contains a higher proportion of ices such as water, ammonia, and methane. Similar to Uranus, its interior is primarily composed of ices and rock. Both planets are normally considered ice giants to distinguish them. Along with Rayleigh scattering, traces of methane in the outermost regions in part account for the planet's blue appearance. Newest data from the Gemini Observatory shows the blue color is more saturated than the one present on Uranus due to the thinner haze of Neptune's more active atmosphere. In contrast to the hazy, relatively featureless atmosphere of Uranus, Neptune's atmosphere has active and visible weather patterns. For example, at the time of the Voyager 2 flyby in 1989, the planet's southern hemisphere had a great dark spot comparable to the Great Red Spot on Jupiter. More recently, in 2018, a newer main dark spot and smaller dark spot were identified and studied. In addition, these weather patterns are driven by the strongest sustained winds of any planet in the Solar System, with recorded wind speeds as high as 2,100 km per hour, 580 m/s, 1,300 miles per hour. Because of its great distance from the Sun, Neptune's outer atmosphere is one of the coldest places in the Solar System, with temperatures at its cloud tops approaching 55 K, 218 degrees C, 361 degree F. Temperatures at the planet's center are approximately 5,400 K, 5,100 degrees Celsius, 9,300 degrees Fahrenheit. Neptune has a faint and fragmented ring system, labeled Arcs, which was discovered in 1984, then later confirmed by Voyager 2. From its discovery in 1846 until the discovery of Pluto in 1930, Neptune was the farthest known planet. When Pluto was discovered, it was considered a planet, and Neptune thus became the second farthest known planet, except for a 20-year period between 1979 and 1999 when Pluto's elliptical orbit brought it closer than Neptune to the Sun, making Neptune the 9th planet from the Sun during this period. The increasingly accurate estimations of Pluto's mass from 10 times that of Earth's to far less than that of the Moon and the discovery of the Kuiper belt in 1992 led many astronomers to debate whether Pluto should be considered a planet or as part of the Kuiper belt. In 2006, the International Astronomical Union defined the word planet for the first time, reclassifying Pluto as a dwarf planet and making Neptune once again the outermost known planet in the Solar System. Neptune's mass of 1.0243 times 1026 kg is intermediate between Earth and the larger gas giants. It is 17 times that of Earth but just 1/19 that of Jupiter. Its gravity at 1 bar is 11.15 m/s2, 1.14 times the surface gravity of Earth, and surpassed only by Jupiter. Neptune's equatorial radius of 24,764 km is nearly 4 times that of Earth. Neptune, like Uranus, is an ice giant, a subclass of giant planet, because they are smaller and have higher concentrations of volatiles than Jupiter and Saturn. In the search for exoplanets, Neptune has been used as a metonym. Discovered bodies of similar mass are often referred. A trace amount of methane is also present. Prominent absorption bands of methane exist at wavelengths above 600 nm, in the red and infrared portion of the spectrum. As with Uranus, this absorption of red light by atmospheric methane is part of what gives Neptune its blue hue 81, although Neptune's blue differs from Uranus's milder light blue. Neptune's atmosphere is subdivided into two main regions, the lower troposphere, where temperature decreases with altitude, and the stratosphere, where temperature increases with altitude. The boundary between the two, the tropopause, lies at a pressure of 0.1 billion Argentine pesos, 10 kPa. The stratosphere then gives way to the thermosphere at a pressure lower than 10.5 to 10.4 bars, 1 to 10 Pa. The thermosphere gradually transitions to the exosphere. Bands of high-altitude clouds cast shadows on Neptune's lower cloud deck. Models suggest that Neptune's troposphere is banded by clouds of varying compositions depending on altitude. The upper-level clouds lie at pressures below 1 bar, where the temperature is suitable for methane to condense. For pressures between 1 and 5 bars, 100 and 500 kPa, clouds of ammonia and hydrogen sulfide are thought to form. Above a pressure of 5 bars, the clouds may consist of ammonia, ammonium sulfide, hydrogen sulfide, and water. Deeper clouds of water ice should be found at pressures of about 50 billion Argentine pesos, 5.0 MPa, where the temperature reaches 273 K, 0 degrees Celsius. Underneath, clouds of ammonia and hydrogen sulfide may be found. High-altitude clouds on Neptune have been observed casting shadows on the opaque cloud deck below. There are also high-altitude cloud bands that wrap around the planet at constant latitudes. These circumferential bands have widths of 5150 km and lie about 5110 km above the cloud deck. These altitudes are in the layer where weather occurs, the troposphere. Weather does not occur in the higher stratosphere or thermosphere. In August 2023, the clouds of Neptune vanished, possibly due to solar flare. 30 years of observations by Hubble Space Telescope and ground-based telescopes showed that Neptune's cloud activity is bound to solar cycles, and not to the planet's seasons. Neptune's spectra suggest that its lower stratosphere is hazy due to condensation of products of ultraviolet photolysis of methane, such as ethane and ethene. The stratosphere is also home to trace amounts of carbon monoxide and hydrogen cyanide. The stratosphere of Neptune is warmer than that of Uranus due to the elevated concentration of hydrocarbons. For reasons that remain obscure, the planet's thermosphere is at an anomalously high temperature of about 750 K. The planet is too far from the Sun for this heat to be generated by ultraviolet radiation. One candidate for a heating mechanism is atmospheric interaction with ions in the planet's magnetic field. Other candidates are gravity waves from the interior that dissipate in the atmosphere. The thermosphere contains traces of carbon dioxide and water, which may have been deposited from external sources such as meteorites and dust. Neptune resembles Uranus in its magnetosphere, with the magnetic field strongly tilted relative to its rotational axis at 47 degrees and offset at least 0.55 radius, or about 13,500 kilometers from the planet's physical center. Before Voyager 2's arrival at Neptune, it was hypothesized that Uranus's tilted magnetosphere was the result of its sideways rotation. In comparing the magnetic fields of the two planets, scientists now think the extreme orientation may be characteristic of flows in the planet's interiors. This field may be generated by convective fluid motions in a thin spherical shell of electrically conducting liquids, probably a combination of ammonia, methane, and water, resulting in a dynamo action. The dipole component of the magnetic field at the magnetic equator of Neptune is about 14 microteslas, 0.14 G. The dipole magnetic moment of Neptune is about 2.2 times 1017 Tm3, 14 mu Trn3, where Rn is the radius of Neptune. Neptune's magnetic field has a complex geometry that includes relatively large contributions from non-dipolar components, including a strong quadrupole moment that may exceed the dipole moment in strength. By contrast, Earth, Jupiter, and Saturn have only relatively small quadrupole moments, and their fields are less tilted from the polar axis. The large quadrupole moment of Neptune may be the result of an offset from the planet's center and geometrical constraints of the field's dynamo generator. Neptune's bow shock, where the magnetosphere begins to slow the solar wind, occurs at a distance of 34.9 times the radius of the planet. The magnetopause, where the pressure of the magnetosphere counterbalances the solar wind, lies at a distance of 26.5 times the radius of Neptune. The tail of the magnetosphere extends out to at least 72 times the radius of Neptune, and likely much farther. The Great Dark Spot, top, scooter, middle white cloud, and the Small Dark Spot, bottom, with contrast exaggerated. Neptune's weather is characterized by extremely dynamic storm systems, with winds reaching speeds of almost 600 m/s, 2,200 km per hour, 1,300 miles per hour, exceeding supersonic flow. More typically, by tracking the motion of persistent clouds, wind speeds have been shown to vary from 20 m/s in the easterly direction to 325 m/s westward. At the cloud tops, the prevailing winds range in speed from 400 m/s along the equator to 250 m/s at the poles. Most of the winds on Neptune move in a direction opposite the planet's rotation. The general pattern of winds showed prograde rotation at high latitudes versus retrograde rotation at lower latitudes. The difference in flow direction is thought to be a skin effect and not due to any deeper atmospheric processes. At 70 degrees south latitude, a high-speed jet travels at a speed of 300 m/s. Neptune differs from Uranus in its typical level of meteorological activity. Voyager 2 observed weather phenomena on Neptune during its 1989 flyby, but no comparable phenomena on Uranus during its 1986 flyby. The abundance of methane, ethane, and acetylene at Neptune's equator is 10-100 times greater than at the poles. This is interpreted as evidence for upwelling at the equator and subsidence near the poles because photochemistry cannot account for the distribution without meridional circulation. In 2007, it was discovered that the upper troposphere of Neptune's south pole was about 10 K warmer than the rest of its atmosphere, which averages approximately 73 K, 200 degrees C. The temperature differential is enough to let methane, which elsewhere is frozen in the troposphere, escape into the stratosphere near the pole. The relative hot spot is due to Neptune's axial tilt, which has exposed the south pole to the Sun for the last quarter of Neptune's year, or roughly 40 Earth years. As Neptune slowly moves towards the opposite side of the Sun, the south pole will be darkened and the north pole illuminated, causing the methane release to shift to the north pole. Because of seasonal changes, the cloud bands in the southern hemisphere of Neptune have been observed to increase in size and albedo. This trend was first seen in 1980. The long orbital period of Neptune results in seasons lasting 40 years. In 1989, the Great Dark Spot, an anticyclonic storm system spanning 13,000 kilometers times 6,600 kilometers, 8,100 miles times 4,100 miles, was discovered by NASA's Voyager 2 spacecraft. The storm resembled the Great Red Spot of Jupiter. Some 5 years later, on November 2, 1994, the Hubble Space Telescope did not see the Great Dark Spot on the planet. Instead, a new storm similar to the Great Dark Spot was found in Neptune's northern hemisphere. The Scooter is another storm, a white cloud group farther south than the Great Dark Spot. This nickname first arose during the months leading up to the Voyager 2 encounter in 1989, when they were observed moving at speeds faster than the Great Dark Spot, and images acquired later would subsequently reveal the presence of clouds moving even faster than those that had initially been detected by Voyager 2. The small dark spot is a southern cyclonic storm, the second most intense storm observed during the 1989 encounter. It was initially completely dark, but as Voyager 2 approached the planet, a bright core developed and can be seen in most of the highest resolution images. More recently, in 2018, a newer main dark spot and smaller dark spot were identified and studied. In 2023, the first ground-based observation of a dark spot on Neptune was announced. Neptune's dark spots are thought to occur in the troposphere at lower altitudes than the brighter cloud features, so they appear as holes in the upper cloud decks. As they are stable features that can persist for several months, they are thought to be vortex structures. Often associated with dark spots are brighter, persistent methane clouds that form around the tropopause layer. The persistence of companion clouds shows that some former dark spots may continue to exist as cyclones even though they are no longer visible as a dark feature. Dark spots may dissipate when they migrate too close to the equator or possibly through some other, unknown mechanism. Neptune's more varied weather when compared to Uranus is due in part to its higher internal heating. The upper regions of Neptune's troposphere reach a low temperature of 51.8 K, 221.3 degrees C. At a depth where the atmospheric pressure equals 1 bar, 100 kPa, the temperature is 72.00 K, 201.15 degrees C. Deeper inside the layers of gas, the temperature rises steadily. As with Uranus, the source of this heating is unknown, but the discrepancy is larger. Uranus only radiates 1.1 times as much energy as it receives from the Sun, whereas Neptune radiates about 2.61 times as much energy as it receives from the Sunday. Neptune is the farthest planet from the Sun, and lies over 50% farther from the Sun than Uranus, and receives only 40% of its amount of sunlight, yet its internal energy is sufficient to drive the fastest planetary winds seen in the Solar System. Depending on the thermal properties of its interior, the heat left over from Neptune's formation may be sufficient to explain its current heat flow, though it is more difficult to simultaneously explain Uranus's lack of internal heat while preserving the apparent similarity between the two planets. Neptune, red arc, completes one orbit around the Sun, center, for every 164.79 orbits of Earth. The light blue object represents Uranus. The average distance between Neptune and the Sun is 4.5 billion km, about 30.1 astronomical units, and it completes an orbit on average every 164.79 years, subject to a variability of around plus or minus 0.1 years. The perihelion distance is 29.810, the aphelion distance is 30.330. On July 11, 2011, Neptune completed its first full barycentric orbit since its discovery in 1846-116, although it did not appear at its exact discovery position in the sky, because Earth was in a different location in its 365.26-day orbit. Because of the motion of the Sun in relation to the barycenter of the Solar System, on July 11 Neptune was also not at its exact discovery position in relation to the Sun. If the more common heliocentric coordinate system is used, the discovery longitude was reached on July 12, 2011. The elliptical orbit of Neptune is inclined 1.77 degrees compared to that of Earth. The axial tilt of Neptune is 28.32 degrees, which is similar to the tilts of Earth, 23 degrees, and Mars, 25 degrees. As a result, Neptune experiences similar seasonal changes to Earth. The long orbital period of Neptune means that the seasons last for 40 Earth years. Its sidereal rotation period, day, is roughly 16.11 hours. Because its axial tilt is comparable to Earth's, the variation in the length of its day over the course of its long year is not any more extreme. Because Neptune is not a solid body, its atmosphere undergoes differential rotation. The wide equatorial zone rotates with a period of about 18 hours, which is slower than the 16.1-hour rotation of the planet's magnetic field. By contrast, the reverse is true for the polar regions where the rotation period is 12 hours. This differential rotation is the most pronounced of any planet in the solar system, and it results in strong latitudinal wind shear. Neptune's orbit has a profound impact on the region directly beyond it, known as the Kuiper belt. The Kuiper belt is a ring of small icy worlds, similar to the asteroid belt but far larger, extending from Neptune's orbit at 30° out to about 55° from the Sunday. Much in the same way that Jupiter's gravity dominates the asteroid belt, shaping its structure, so Neptune's gravity dominates the Kuiper belt. Over the age of the solar system, certain regions of the Kuiper belt became destabilized by Neptune's gravity, creating gaps in its structure. The region between 40 and 42° is an example. There do exist orbits within these empty regions where objects can survive for the age of the solar system. These resonances occur when Neptune's orbital period is a precise fraction of that of the object, such as 1:2, or 3:4. If, say, an object orbits the Sun once for every 2 Neptune orbits, it will only complete half an orbit by the time Neptune returns to its original position. The most heavily populated resonance in the Kuiper belt, with over 200 known objects, is the 2:3 resonance. Objects in this resonance complete 2 orbits for every 3 of Neptune, and are known as Plutinos because the largest of the known Kuiper belt objects, Pluto, is among them. Although Pluto crosses Neptune's orbit regularly, the 2:3 resonance ensures they can never collide. The 3:4, 3:5, 4:7 and 2:5 resonances are less populated. Neptune has a number of known Trojan objects occupying both the Sun-Neptune L4 and L5 Lagrangian points, gravitationally stable regions leading and trailing Neptune in its orbit, respectively. Neptune Trojans can be viewed as being in a 1:1 resonance with Neptune. Some Neptune Trojans are remarkably stable in their orbits, and are likely to have formed alongside Neptune rather than being captured. The first object identified as associated with Neptune's trailing L5 Lagrangian point was 2008 LC18. Neptune also has a temporary quasi-satellite, 309,239, 2007 RW10. The object has been a quasi-satellite of Neptune for about 12,500 years, and it will remain in that dynamical state for another 12,500 years. A simulation showing the outer planets and Kuiper belt, A, before Jupiter and Saturn reached a 2:1 resonance, B, after inward scattering of Kuiper belt objects following the orbital shift of Neptune, C, after ejection of scattered Kuiper belt bodies by Jupiter. The formation of the ice giants, Neptune and Uranus, has proven difficult to model precisely. Current models suggest that the matter density in the outer regions of the solar system was too low to account for the formation of such large bodies from the traditionally accepted method of core accretion, and various hypotheses have been advanced to explain their formation. One is that the ice giants were not formed by core accretion but from instabilities within the original protoplanetary disk and later had their atmospheres blasted away by radiation from a nearby massive OB star. An alternative concept is that they formed closer to the Sun, where the matter density was higher, and then subsequently migrated to their current orbits after the removal of the gaseous protoplanetary disk. This hypothesis of migration after formation is favored, due to its ability to better explain the occupancy of the populations of small objects observed in the trans-Neptunian region. The current most widely accepted explanation of the details of this hypothesis is known as the NICE model, which explores the effect of a migrating Neptune and the other giant planets on the structure of the Kuiper belt. For a timeline of discovery dates, see Timeline of discovery of solar system planets and their moons. Neptune has 14 known moons. Triton is the largest Neptunian moon, comprising more than 99.5% of the mass in orbit around Neptune, and it is the only one massive enough to be spheroidal. Triton was discovered by William Lassell just 17 days after the discovery of Neptune itself. Unlike all other large planetary moons in the Solar System, Triton has a retrograde orbit, indicating that it was captured rather than forming in place. It was probably once a dwarf planet in the Kuiper belt. It is close enough to Neptune to be locked into a synchronous rotation, and it is slowly spiraling inward because of tidal acceleration. It will eventually be torn apart, in about 3.6 billion years, when it reaches the Roche limit. In 1989, Triton was the coldest object that had yet been measured in the Solar System, with estimated temperatures of 38 K, 235 degrees C. Neptune's second known satellite, by order of discovery, the irregular moon Nereid, has one of the most eccentric orbits of any satellite in the Solar System. The eccentricity of 0.7512 gives it an apoapsis that is 7 times its periapsis distance from Neptune. From July to September 1989, Voyager 2 discovered 6 moons of Neptune. Of these, the irregularly shaped Proteus is notable for being as large as a body of its density can be without being pulled into a spherical shape by its own gravity. Although the second most massive Neptunian moon, it is only 0.25% the mass of Triton. Neptune's innermost 4 moons Naiad, Thalassa, Despina, and Galatea orbit close enough to be within Neptune's rings. The next farthest out, Larissa, was originally discovered in 1981 when it had occulted a star. This occultation had been attributed to ring arcs, but when Voyager 2 observed Neptune in 1989, Larissa was found to have caused it. 5 new irregular moons discovered between 2002 and 2003 were announced in 2004. A new moon and the smallest yet, Hippocamp, was found in 2013 by combining multiple Hubble images. Because Neptune was the Roman god of the sea, Neptune's moons have been named after lesser sea gods. Neptune has a planetary ring system, though one much less substantial than that of Saturn. The rings may consist of ice particles coated with silicates or carbon-based material, which most likely gives them a reddish hue. The 3 main rings are the narrow Adam's ring, 63,000 km from the center of Neptune, the Le Verrier ring, at 53,000 km, and the broader, fainter Gall ring, at 42,000 km. A faint outward extension to the Le Verrier ring has been named Lassell. It is bounded at its outer edge by the Arago ring at 57,000 km. The first of these planetary rings was detected in 1968 by a team led by Edward Ginnern. In the early 1980s, analysis of this data along with newer observations led to the hypothesis that this ring might be incomplete. Evidence that the rings might have gaps first arose during a stellar occultation in 1984 when the rings obscured a star on immersion but not on immersion. Images from Voyager 2 in 1989 settled the issue by showing several faint rings. The outermost ring, Adams, contains 5 prominent arcs now named Courage, Liberté, Égalité 1, Égalité 2 and Fraternité, Courage, Liberty, Equality, and Fraternity. The existence of arcs was difficult to explain because the laws of motion would predict that arcs would spread out into a uniform ring over short time scales. Astronomers now estimate that the arcs are corralled into their current form by the gravitational effects of Galatea, a moon just inward from the ring. Earth-based observations announced in 2005 appeared to show that Neptune's rings were much more unstable than previously thought. Images taken from the W.M. Keck Observatory in 2002 and 2003 show considerable decay in the rings when compared to images by Voyager 2. In particular, it seems that the Liberté arc might disappear in as little as 1 century. Neptune is the 8th planet from the Sun and the farthest IAU-recognized planet in the Solar System. It is the 4th largest planet in the Solar System by diameter, the 3rd. Pluto, minor planet designation, 134,340. Pluto, is a dwarf planet in the Kuiper belt, a ring of bodies beyond the orbit of Neptune. It is the 9th largest and 10th most massive known object to directly orbit the Sunday. It is the largest known trans-Neptunian object by volume, by a small margin, but is slightly less massive than Eris. Like other Kuiper belt objects, Pluto is made primarily of ice and rock and is much smaller than the inner planets. Pluto has only 1/6 the mass of Earth's moon, and 1/3 its volume. Pluto has a moderately eccentric and inclined orbit, ranging from 30 to 49 astronomical units, 4.5 to 7.3 billion kilometers, 2.8 to 4.6 billion miles, from the Sunday. Light from the Sun takes 5.5 hours to reach Pluto at its orbital distance of 39.50, 5.91 billion km, 3.67 billion mi. Pluto's eccentric orbit periodically brings it closer to the Sun than Neptune, but a stable orbital resonance prevents them from colliding. Pluto has 5 known moons: Charon, the largest, whose diameter is just over half that of Pluto, Styx, Nix, Kerberos, and Hydra. Pluto and Charon are sometimes considered a binary system because the barycenter of their orbits does not lie within either body, and they are tidally locked. The New Horizons mission was the first spacecraft to visit Pluto and its moons, making a flyby on July 14, 2015 and taking detailed measurements and observations. Pluto was discovered in 1930 by Clyde W. Tombaugh, the first object in the Kuiper belt. It was immediately hailed as the 9th planet, but it was always the odd object out 14, 27 and its planetary status was questioned when it was found to be much smaller than expected. These doubts increased following the discovery of additional objects in the Kuiper belt starting in the 1990s, and particularly the more massive scattered disk object Eris in 2005. In 2006, the International Astronomical Union, IAU, formally redefined the term planet to exclude dwarf planets such as Pluto. Many planetary astronomers, however, continue to consider Pluto and other dwarf planets to be planets. In the 1840s, Urbain Le Verrier used Newtonian mechanics to predict the position of the then undiscovered planet Neptune after analyzing perturbations in the orbit of Uranus. Subsequent observations of Neptune in the late 19th century led astronomers to speculate that Uranus's orbit was being disturbed by another planet besides Neptune. In 1906, Percival Lowell, a wealthy Bostonian who had founded Lowell Observatory in Flagstaff, Arizona, in 1894 started an extensive project in search of a possible 9th planet, which he termed Planet X. By 1909, Lowell and William H. Pickering had suggested several possible celestial coordinates for such a planet. Lowell and his observatory conducted his search, using mathematical calculations made by Elizabeth Williams, until his death in 1916, but to no avail. Unknown to Lowell, his surveys had captured 2 faint images of Pluto on March 19 and April 7, 1915, but they were not recognized for what they were. There are 14 other known Precovery observations, with the earliest made by the Yerkes Observatory on August 20, 1909. Percival's widow, Constance Lowell, entered into a 10-year legal battle with the Lowell Observatory over her husband's legacy, and the search for Planet X did not resume until 1929. Vesto Melvin Slifer, the observatory director, gave the job of locating Planet X to 23-year-old Clyde Tombaugh, who had just arrived at the observatory after Slifer had been impressed by a sample of his astronomical drawings. Tombaugh's task was to systematically image the night sky in pairs of photographs, then examine each pair and determine whether any objects had shifted position. Using a blink comparator, he rapidly shifted back and forth between views of each of the plates to create the illusion of movement of any objects that had changed position or appearance between photographs. On February 18, 1930, after nearly a year of searching, Tombaugh discovered a possible moving object on photographic plates taken on January 23 and 29. A lesser quality photograph taken on January 21 helped confirm the movement. After the observatory obtained further confirmatory photographs, news of the discovery was telegraphed to the Harvard College Observatory on March 13, 1930. As 1 Plutonian year corresponds to 247.94 Earth years, in 2178, Pluto will complete its first orbit since its discovery. Once Pluto was found, its faintness and lack of a viewable disk cast doubt on the idea that it was Lowell's Planet X. Estimates of Pluto's mass were revised downward throughout the 20th century. Astronomers initially calculated its mass based on its presumed effect on Neptune and Uranus. In 1931, Pluto was calculated to be roughly the mass of Earth, with further calculations in 1948 bringing the mass down to roughly that of Mars. In 1976, Dale Cruikshank, Carl Pilcher and David Morrison of the University of Hawaii calculated Pluto's albedo for the first time, finding that it matched that for methane ice. This meant Pluto had to be exceptionally luminous for its size and therefore could not be more than 1% the mass of Earth. Pluto's albedo is 1.41.9 times that of Earth. In 1978, the discovery of Pluto's moon Charon allowed the measurement of Pluto's mass for the first time, roughly 0.2% that of Earth, and far too small to account for the discrepancies in the orbit of Uranus. Subsequent searches for an alternative planet X, notably by Robert Sutton Harrington, failed. In 1992, Miles Standish used data from Voyager 2's flyby of Neptune in 1989, which had revised the estimates of Neptune's mass downward by 0.5%, an amount comparable to the mass of Mars, to recalculate its gravitational effect on Uranus. With the new figures added in, the discrepancies, and with them the need for a planet X, vanished. As of 2000, the majority of scientists agree that Planet X, as Lowell defined it, does not exist. Lowell had made a prediction of Planet X's orbit and position in 1915 that was fairly close to Pluto's actual orbit and its position at that time. Ernest W. Brown concluded soon after Pluto's discovery that this was a coincidence. Artistic comparison of Pluto, Eris, Haumea, Make, Gong Gong, Quaoar, Sedna, Orcus, Salacia, 2002 MS4, and Earth along with the Moon Vite. From 1992 onward, many bodies were discovered orbiting in the same volume as Pluto, showing that Pluto is part of a population of objects called the Kuiper Belt. This made its official status as a planet controversial, with many questioning whether Pluto should be considered together with or separately from its surrounding population. Museum and planetarium directors occasionally created controversy by omitting Pluto from planetary models of the solar system. In February 2000, the Hayden Planetarium in New York City displayed a solar system model of only 8 planets, which made headlines almost a year later. Ceres, Pallas, Juno, and Vesta lost their planet status after the discovery of many other asteroids. Similarly, objects increasingly closer in size to Pluto were discovered in the Kuiper Belt region. On July 29, 2005, astronomers at Caltech announced the discovery of a new trans-Neptunian object, Eris, which was substantially more massive than Pluto and the most massive object discovered in the solar system since Triton in 1846. Its discoverers and the press initially called it the 10th planet, although there was no official consensus at the time on whether to call it a planet. Others in the astronomical community considered the discovery the strongest argument for reclassifying Pluto as a minor planet. The debate came to a head in August 2006, with an IAU resolution that created an official definition for the term planet. According to this resolution, there are 3 conditions for an object in the solar system to be considered a planet. The object must be in orbit around the Sunday. The object must be massive enough to be rounded by its own gravity. More specifically, its own gravity should pull it into a shape defined by hydrostatic equilibrium. It must have cleared the neighborhood around its orbit. Pluto fails to meet the third condition. Its mass is substantially less than the combined mass of the other objects in its orbit, 0.07 times, in contrast to Earth, which is 1.7 million times the remaining mass in its orbit, excluding the Moon. The IAU further decided that bodies that, like Pluto, meet criteria 1 and 2, but do not meet criterion 3 would be called dwarf planets. In September 2006, the IAU included Pluto and Eris and its moon Dysnomia in their minor planet catalog, giving them the official minor planet designations: 134,340, Pluto, 136,199, Eris, and 136,199, Erisi Dysnomia. Had Pluto been included upon its discovery in 1930, it would have likely been designated 1164, following 1163 Saga, which was discovered a month earlier. There has been some resistance within the astronomical community toward the reclassification. Alan Stern, principal investigator with NASA's New Horizons mission to Pluto, derided the IAU resolution. He also stated that because less than 5% of astronomers voted for it, the decision was not representative of the entire astronomical community. Mark W. Buie, then at the Lowell Observatory, petitioned against the definition. Others have supported the IAU, for example Mike Brown, the astronomer who discovered Eris. Public reception to the IAU decision was mixed. A resolution introduced in the California State Assembly facetiously called the IAU decision a scientific heresy. The New Mexico House of Representatives passed a resolution in honor of Clyde Tombaugh, the discoverer of Pluto and a longtime resident of that state, that declared that Pluto will always be considered a planet while in New Mexican skies and that March 13, 2007, was Pluto Planet Day. The Illinois Senate passed a similar resolution in 2009 on the basis that Tombaugh was born in Illinois. The resolution asserted that Pluto was unfairly downgraded to a dwarf planet by the IAU. Some members of the public have also rejected the change, citing the disagreement within the scientific community on the issue, or for sentimental reasons, maintaining that they have always known Pluto as a planet and will continue to do so regardless of the IAU decision. In 2006, in its 17th annual Words of the Year vote, the American Dialect Society voted Pluto as the word of the year. To Pluto is to demote or devalue someone or something. Researchers on both sides of the debate gathered in August 2008, at the Johns Hopkins University Applied Physics Laboratory for a conference that included back-to-back talks on the IAU definition of a planet. Entitled The Great Planet Debate, the conference published a post-conference press release indicating that scientists could not come to a consensus about the definition of planet. In June 2008, the IAU had announced in a press release that the term Plutoid would henceforth be used to refer to Pluto and other planetary mass objects that have an orbital semi-major axis greater than that of Neptune, though the term has not seen significant use. Pluto's orbital period is about 248 years. Its orbital characteristics are substantially different from those of the planets, which follow nearly circular orbits around the Sun close to a flat reference plane called the ecliptic. In contrast, Pluto's orbit is moderately inclined relative to the ecliptic, over 17 degrees, and moderately eccentric, elliptical. This eccentricity means a small region of Pluto's orbit lies closer to the Sun than Neptune's. The Pluto Karen Berry Center came to perihelion on September 5, 1989, and was last closer to the Sun than Neptune between February 7, 1979, and February 11, 1999. Although the 3:2 resonance with Neptune, see below, is maintained, Pluto's inclination and eccentricity behave in a chaotic manner. Computer simulations can be used to predict its position for several million years, both forward and backward in time, but after intervals much longer than the Lyapunov time of 10-20 million years, calculations become unreliable. Pluto is sensitive to immeasurably small details of the solar system, hard to predict factors that will gradually change Pluto's position in its orbit. The semi-major axis of Pluto's orbit varies between about 39.3 and 39.60 with a period of about 19,951 years, corresponding to an orbital period varying between 246 and 249 years. The semi-major axis and period are presently getting longer. Despite Pluto's orbit appearing to cross that of Neptune when viewed from directly above, the two objects' orbits do not intersect. When Pluto is closest to the Sun, and close to Neptune's orbit as viewed from above, it is also the farthest above Neptune's path. Pluto's orbit passes about 80 above that of Neptune, preventing a collision. This alone is not enough to protect Pluto. Perturbations from the planets, especially Neptune, could alter Pluto's orbit, such as its orbital precession, over millions of years so that a collision could be possible. However, Pluto is also protected by its 2:3 orbital resonance with Neptune, For every 2 orbits that Pluto makes around the Sun, Neptune makes 3. Each cycle lasts about 495 years. There are many other objects in this same resonance, called Plutinos. This pattern is such that, in each 495-year cycle, the first time Pluto is near perihelion, Neptune is over 50 degrees behind Pluto. By Pluto's second perihelion, Neptune will have completed a further 1.5 of its own orbits, and so will be nearly 130 degrees ahead of Pluto. Pluto and Neptune's minimum separation is over 17.0, which is greater than Pluto's minimum separation from Uranus, 11.0. The minimum separation between Pluto and Neptune actually occurs near the time of Pluto's aphelion. The 2:3 resonance between the two bodies is highly stable and has been preserved over millions of years. This prevents their orbits from changing relative to one another, and so the two bodies can never pass near each other. Even if Pluto's orbit were not inclined, the two bodies could never collide. The long-term stability of the mean motion resonance is due to phase protection. When Pluto's period is slightly shorter than 3/2 of Neptune, its orbit relative to Neptune will drift, causing it to make closer approaches behind Neptune's orbit. The gravitational pull between the two then causes angular momentum to be transferred to Pluto, at Neptune's expense. This moves Pluto into a slightly larger orbit, where it travels slightly more slowly, according to Kepler's third law. After many such repetitions, Pluto is sufficiently slowed that Pluto's orbit relative to Neptune drifts in the opposite direction until the process is reversed. The whole process takes about 20,000 years to complete. Numerical studies have shown that over millions of years, the general nature of the alignment between the orbits of Pluto and Neptune does not change. There are several other resonances and interactions that enhance Pluto's stability. These arise principally from 2 additional mechanisms, besides the 2:3 mean motion resonance. First, Pluto's argument of perihelion, the angle between the point where it crosses the ecliptic and the point where it is closest to the Sun, librates around 90 degrees. This means that when Pluto is closest to the Sun, it is at its farthest above the plane of the solar system, preventing encounters with Neptune. This is a consequence of the Cauchy mechanism, which relates the eccentricity of an orbit to its inclination to a larger perturbing body, in this case, Neptune. Relative to Neptune, the amplitude of libration is 38 degrees, and so the angular separation of Pluto's perihelion to the orbit of Neptune is always greater than 52 degrees, 90 degree 38 degree. The closest such angular separation occurs every 10,000 years. Second, the longitudes of ascending nodes of the two bodies, the points where they cross the ecliptic, are in near resonance with the above libration. When the two longitudes are the same, that is, when one could draw a straight line through both nodes and the Sun, Pluto's perihelion lies exactly at 90 degrees, and hence it comes closest to the Sun when it is highest above Neptune's orbit. This is known as the 1:1 super resonance. All the Jovian planets, particularly Jupiter, play a role in the creation of the super resonance. Pluto's rotation period, its day, is equal to 6.387 Earth days. Like Uranus and 2 Pallas, Pluto rotates on its side in its orbital plane, with an axial tilt of 120 degrees, and so its seasonal variation is extreme. At its solstices, 1/4 of its surface is in continuous daylight, whereas another 1/4 is in continuous darkness. The reason for this unusual orientation has been debated. Research from the University of Arizona has suggested that it may be due to the way that a body's spin will always adjust to minimize energy. This could mean a body reorienting itself to put extraneous mass near the equator and regions lacking mass tend towards the poles. This is called polar wander. According to a paper released from the University of Arizona, this could be caused by masses of frozen nitrogen building up in shadowed areas of the dwarf planet. These masses would cause the body to reorient itself, leading to its unusual axial tilt of 120 degrees. The buildup of nitrogen is due to Pluto's vast distance from the Sun. At the equator, temperatures can drop to 240 degrees C, 400.0 degree F, 33.1 K, causing nitrogen to freeze as water would freeze on Earth. The same effect seen on Pluto would be observed on Earth were the Antarctic ice sheet several times larger. Sputnik Planitia is covered with churning nitrogen ice cells that are geologically young and turning over due to convection. The plains on Pluto's surface are composed of more than 98% nitrogen ice, with traces of methane and carbon monoxide. Nitrogen and carbon monoxide are most abundant on the Anticharon face of Pluto, around 180 degrees longitude, where Tomboregio's western lobe, Sputnik Planitia, is located, whereas methane is most abundant near 300 degrees east. The mountains are made of water ice. Pluto's surface is quite varied, with large differences in both brightness and color. Pluto is one of the most contrastive bodies in the solar system, with as much contrast as Saturn's moon Iapetus. The color varies from charcoal black to dark orange and white. Pluto's color is more similar to that of Io, with slightly more orange and significantly less red than Mars. Notable geographical features include Tomboregio, or the heart, a large bright area on the side opposite Charon, Fulha Macula, or the whale, a large dark area on the trailing hemisphere, and the brass knuckles, a series of equatorial dark areas on the leading hemisphere. Sputnik Planitia, the western lobe of the heart, is a 1,000 km wide basin of frozen nitrogen and carbon monoxide ices, divided into polygonal cells, which are interpreted as convection cells that carry floating blocks of water ice crust and sublimation pits towards their margins. There are obvious signs of glacial flows both into and out of the basin. It has no craters that were visible to New Horizons, indicating that its surface is less than 10 million years old. Latest studies have shown that the surface has an age of 180000 plus 90,000–40,000 years. The New Horizons science team summarized initial findings as Pluto displays a surprisingly wide variety of geological landforms, including those resulting from glaciological and surface-atmosphere interactions as well as impact, tectonic, possible cryovolcanic, and mass-wasting processes. In western parts of Sputnik Planitia there are fields of transverse dunes formed by the winds blowing from the center of Sputnik Planitia in the direction of surrounding mountains. The dune wavelengths are in the range of 0.41 km and likely consist of methane particles 200–300 μm in size. Distribution of over 1,000 craters of all ages in the northern Anticharon quadrant of Pluto. The variation in density, with none found in Sputnik Planitia, indicates a long history of varying geological activity. The lack of crater on the left and right of the map is due to low-resolution coverage of those subcharon regions. Distribution of over 1,000 craters of all ages in the northern Anticharon quadrant of Pluto. The variation in density, with none found in Sputnik Planitia, indicates a long history of varying geological activity. The lack of crater on the left and right of the map is due to low-resolution coverage of those subcharon regions. Pluto's density is 1.860 plus or minus 0.013 g/cm3. Because the decay of radioactive elements would eventually heat the ices enough for the rock to separate from them, scientists expect that Pluto's internal structure is differentiated, with the rocky material having settled into a dense core surrounded by a mantle of water ice. The pre-New Horizons estimate for the diameter of the core is 1,700 kilometers, 70% of Pluto's diameter. Pluto has no magnetic field. It is possible that such heating continues, creating a subsurface ocean of liquid water 100 to 180 kilometers thick at the core mantle boundary. In September 2016, scientists at Brown University simulated the impact thought to have formed Sputnik Planitia, and showed that it might have been the result of liquid water upwelling from below after the collision, implying the existence of a subsurface ocean at least 100 kilometers deep. In June 2020, astronomers reported evidence that Pluto may have had a subsurface ocean, and consequently may have been habitable, when it was first formed. In March 2022, they concluded that peaks on Pluto are actually a merger of ice volcanoes, suggesting a source of heat on the body at levels previously thought not possible. Pluto's diameter is 2376.6 plus or minus 3.2 km and its mass is 1.303 plus or minus 0.003 times 1022 kg, 17.7% that of the Moon, 0.22% that of Earth. Its surface area is 1.774443 times 107 km2, or just slightly bigger than Russia or Antarctica. Its surface gravity is 0.063 grams, compared to 1 gram for Earth and 0.17 grams for the Moon. The discovery of Pluto's satellite Charon in 1978 enabled a determination of the mass of the Pluto-Charon system by application of Newton's formulation of Kepler's third law. Observations of Pluto in occultation with Charon allowed scientists to establish Pluto's diameter more accurately, whereas the invention of adaptive optics allowed them to determine its shape more accurately. With less than 0.2 lunar masses, Pluto is much less massive than the terrestrial planets, and also less massive than 7 moons, Ganymede, Titan, Callisto, Io, the Moon, Europa, and Triton. The mass is much less than thought before Charon was discovered. Pluto is more than twice the diameter and a dozen times the mass of Ceres, the largest object in the asteroid belt. It is less massive than the dwarf planet Eris, a trans-Neptunian object discovered in 2005, though Pluto has a larger diameter of 2,376.6 km compared to Eris's approximate diameter of 2,326 km. Determinations of Pluto's size have been complicated by its atmosphere and hydrocarbon haze. In March 2014, Lelouch, de Berg et al. Published findings regarding methane mixing ratios in Pluto's atmosphere consistent with a Plutonian diameter greater than 2,360 km, with a best guess of 2,368 km. On July 13, 2015, images from NASA's New Horizons mission Long Range Reconnaissance Imager, LORRI, along with data from the other instruments, determined Pluto's diameter to be 2,370 km, 1,470 miles, which was later revised to be 2,372 km, 1,474 miles, on July 24, and later to 2,374 plus or minus 8 km. Using radio occultation data from the New Horizons Radio Science Experiment, REX, the diameter was found to be 2376.6 plus or minus 3.2 km. Pluto has a tenuous atmosphere consisting of nitrogen, N2, methane, CH4, and carbon monoxide, CO, which are in equilibrium with their ices on Pluto's surface. According to the measurements by New Horizons, the surface pressure is about 1 Pa, 10 bar, roughly 1 million to 100,000 times less than Earth's atmospheric pressure. It was initially thought that, as Pluto moves away from the Sun, its atmosphere should gradually freeze onto the surface. Studies of New Horizons data and ground-based occultations show that Pluto's atmospheric density increases, and that it likely remains gaseous throughout Pluto's orbit. New Horizons observations showed that atmospheric escape of nitrogen to be 10,000 times less than expected. Alan Stern has contended that even a small increase in Pluto's surface temperature can lead to exponential increases in Pluto's atmospheric density, from 18 HPa to as much as 280 HPa, 3 times that of Mars to a quarter that of the Earth. At such densities, nitrogen could flow across the surface as liquid. Just like sweat cools the body as it evaporates from the skin, the sublimation of Pluto's atmosphere cools its surface. Pluto has no or almost no troposphere. Observations by New Horizons suggest only a thin tropospheric boundary layer. Its thickness in the place of measurement was 4 km, and the temperature was 37 plus or minus 3 K. The layer is not continuous. In July 2019, an occultation by Pluto showed that its atmospheric pressure, against expectations, had fallen by 20% since 2016. In 2021, astronomers at the Southwest Research Institute confirmed the result using data from an occultation in 2018, which showed that light was appearing less gradually from behind Pluto's disk, indicating a thinning atmosphere. The presence of methane, a powerful greenhouse gas, in Pluto's atmosphere creates a temperature inversion, with the average temperature of its atmosphere tens of degrees warmer than its surface. Though observations by New Horizons have revealed Pluto's upper atmosphere to be far colder than expected, 70 K, as opposed to about 100 K. Pluto's atmosphere is divided into roughly 20 regularly spaced haze layers up to 150 kilometers high, thought to be the result of pressure waves created by airflow across Pluto's mountains. Pluto has 5 known natural satellites. The closest to Pluto is Charon. First identified in 1978 by astronomer James Christie, Charon is the only moon of Pluto that may be in hydrostatic equilibrium. Charon's mass is sufficient to cause the barycenter of the Pluto-Charon system to be outside Pluto. Beyond Charon there are 4 much smaller circumbinary moons. In order of distance from Pluto they are Styx, Nix, Kerberos, and Hydra. Nix and Hydra were both discovered in 2005, Kerberos was discovered in 2011, and Styx was discovered in 2012. The satellites' orbits are circular, eccentricity 0.006, and coplanar with Pluto's equator, inclination 1 degree, and therefore tilted approximately 120 degrees relative to Pluto's orbit. The Plutonian system is highly compact. The 5 known satellites orbit within the inner 3% of the region where prograde orbits would be stable. The orbital periods of all Pluto's moons are linked in a system of orbital resonances and near resonances. When precession is accounted for, the orbital periods of Styx, Nix, and Hydra are in an exact 18 hours 22 minutes and 33 seconds ratio. There is a sequence of approximate ratios, 3:4:5:6, between the periods of Styx, Nix, Kerberos, and Hydra with that of Charon. The ratios become closer to being exact the further out the moons are. The Pluto-Charon system is one of the few in the Solar System whose barycenter lies outside the primary body. The Patroclus-Mennoetius system is a smaller example, and the Sun-Jupiter system is the only larger one. The similarity in size of Charon and Pluto has prompted some astronomers to call it a double dwarf planet. The system is also unusual among planetary systems in that each is tidally locked to the other, which means that Pluto and Charon always have the same hemisphere facing each other, a property shared by only one other known system, Eris and dysnomia. From any position on either body, the other is always at the same position in the sky, or always obscured. This also means that the rotation period of each is equal to the time it takes the entire system to rotate around its barycenter. In 2007, observations by the Gemini Observatory of patches of ammonia hydrates and water crystals on the surface of Charon suggested the presence of active cryogeysers. Pluto's moons are hypothesized to have been formed by a collision between Pluto and a similar-sized body, early in the history of the Solar System. The collision released material that consolidated into the moons around Pluto. In 2012, it was calculated that 15,810 Eris could be a quasi-satellite of Pluto, a specific type of CO orbital configuration. According to the calculations, the object would be a quasi-satellite of Pluto for about 350,000 years out of every 2 million year period. Measurements made by the New Horizons spacecraft in 2015 made it possible to calculate the orbit of Eris more accurately, and confirmed the earlier ones. However, it is not agreed upon among astronomers whether Eris should be classified as a quasi-satellite of Pluto based on its orbital dynamics, since its orbit is primarily controlled by Neptune with only occasional perturbations by Pluto. Pluto's origin and identity had long puzzled astronomers. One early hypothesis was that Pluto was an escaped moon of Neptune knocked out of orbit by Neptune's largest moon, Triton. This idea was eventually rejected after dynamical studies showed it to be impossible because Pluto never approaches Neptune in its orbit. Pluto's true place in the Solar System began to reveal itself only in 1992, when astronomers began to find small icy objects beyond Neptune that were similar to Pluto not only in orbit but also in size and composition. This trans-Neptunian population is thought to be the source of many short-period comets. Pluto is the largest member of the Kuiper belt, a stable belt of objects located between 30 and 50 O from the Sunday. As of 2011, surveys of the Kuiper belt to magnitude 21 were nearly complete and any remaining Pluto-sized objects are expected to be beyond 100 O from the Sunday. Like other Kuiper belt objects, KBOs, Pluto shares features with comets. For example, the solar wind is gradually blowing Pluto's surface into space. It has been claimed that if Pluto were placed as near to the Sun as Earth, it would develop a tail, as comets do. This claim has been disputed with the argument that Pluto's escape velocity is too high for this to happen. It has been proposed that Pluto may have formed as a result of the agglomeration of numerous comets and Kuiper belt objects. Though Pluto is the largest Kuiper belt object discovered, Neptune's moon Triton, which is larger than Pluto, is similar to it both geologically and atmospherically, and is thought to be a captured Kuiper belt object. Eris, see above, is about the same size as Pluto, though more massive, but is not strictly considered a member of the Kuiper belt population. Rather, it is considered a member of a linked population called the scattered disk. Many Kuiper belt objects, like Pluto, are in a 2:3 orbital resonance with Neptune. KBOs with this orbital resonance are called Plutinos, after Pluto. Like other members of the Kuiper belt, Pluto is thought to be a residual planetesimal, a component of the original protoplanetary disk around the Sun that failed to fully coalesce into a full-fledged planet. Most astronomers agree that Pluto owes its position to a sudden migration undergone by Neptune early in the Solar System's formation. As Neptune migrated outward, it approached the objects in the Proto-Kuiper belt, setting one in orbit around itself, Triton, locking others into resonances, and knocking others into chaotic orbits. The objects in the scattered disk, a dynamically unstable region overlapping the Kuiper belt, are thought to have been placed in their positions by interactions with Neptune's migrating resonances. A computer model created in 2004 by Alessandro Morbidelli of the Observatoire de la Côte d'Azur in Nice suggested that the migration of Neptune into the Kuiper belt may have been triggered by the formation of a 1:2 resonance between Jupiter and Saturn, which created a gravitational push that propelled both Uranus and Neptune into higher orbits and caused them to switch places, ultimately doubling Neptune's distance from the Sunday. The resultant expulsion of objects from the Proto-Kuiper belt could also explain the late heavy bombardment 600 million years after the Solar System's formation and the origin of the Jupiter Trojans. It is possible that Pluto had a near-circular orbit about 33° from the Sun before Neptune's migration perturbed it into a resonan. Pluto, minor planet designation, 134,340 Pluto, is a dwarf planet in the Kuiper belt, a ring of bodies beyond the orbit of Neptune. It is the 9th largest and 10th most massive known object to directly orbit the Sunday. It is the largest known trans-Neptunian object by volume, by a small margin, but is slightly. Ceres is a minor planet designation. 1 Ceres is a dwarf planet in the asteroid belt between the orbits of Mars and Jupiter. It was the first asteroid discovered, on January 1, 1801, by Giuseppe Piazzi at Palermo Astronomical Observatory in Sicily and announced as a new planet. Ceres was later classified as an asteroid and then a dwarf planet, the only one always inside Neptune's orbit. Ceres's small size means that even at its brightest, it is too dim to be seen by the naked eye, except under extremely dark skies. Its apparent magnitude ranges from 6.7 to 9.3, peaking at opposition, when it is closest to Earth, once every 15 to 16 month synodic period. As a result, its surface features are barely visible even with the most powerful telescopes, and little was known about it until the robotic NASA spacecraft Dawn approached Ceres for its orbital mission in 2015. Dawn found Ceres's surface to be a mixture of water ice and hydrated minerals such as carbonates and clay. Gravity data suggest Ceres to be partially differentiated into a muddy, ice rock, mantle/core and a less dense but stronger crust that is at most 30% ice by volume. Although Ceres likely lacks an internal ocean of liquid water, brines still flow through the outer mantle and reach the surface, allowing cryovolcanoes such as Ahuna Mons to form roughly every 50 million years. This makes Ceres the closest known cryovolcanic body to the Sun, and the brines provide a potential habitat for microbial life. In January 2014, emissions of water vapor were detected around Ceres, creating a tenuous, transient atmosphere known as an exosphere. This was unexpected because vapor is usually a hallmark of comets, not asteroids. The categorization of Ceres has changed more than once and has been the subject of some disagreement. Bode believed Ceres to be the missing planet he had proposed to exist between Mars and Jupiter. Ceres was assigned a planetary symbol and remained listed as a planet in astronomy books and tables, along with Pallas, Juno, and Vesta, for over half a century. As other objects were discovered in the neighborhood of Ceres, astronomers began to suspect that it represented the first of a new class of objects. When Pallas was discovered in 1802, Herschel coined the term asteroid, star-like, for these bodies, writing that they resemble small stars so much as hardly to be distinguished from them, even by very good telescopes. In 1852 Johann Franz Encke, in the Berliner Astronomisches Jahrbuch, declared the traditional system of granting planetary symbols too cumbersome for these new objects and introduced a new method of placing numbers before their names in order of discovery. Initially, the numbering system began with the fifth asteroid, 5 Astrea, as number 1, but in 1867 Ceres was adopted into the new system under the name 1 Ceres. By the 1860s, astronomers widely accepted that a fundamental difference existed between the major planets and asteroids such as Ceres, though the word planet had yet to be precisely defined. In the 1950s, scientists generally stopped considering most asteroids as planets, but Ceres sometimes retained its status after that because of its planet-like geophysical complexity. Then, in 2006, the debate surrounding Pluto led to calls for a definition of planet, and the possible reclassification of Ceres, perhaps even its general reinstatement as a planet. A proposal before the International Astronomical Union, IAU, the global body responsible for astronomical nomenclature and classification, defined a planet as a celestial body that, a, has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round, shape, and, b, is in orbit around a star, and is neither a star nor a satellite of a planet. Had this resolution been adopted, it would have made Ceres the fifth planet in order from the Sun, but on August 24, 2006 the Assembly adopted the additional requirement that a planet must have cleared the neighborhood around its orbit. Ceres is not a planet because it does not dominate its orbit, sharing it as it does with the thousands of other asteroids in the asteroid belt and constituting only about 40% of the belt's total mass. Bodies that met the first proposed definition but not the second, such as Ceres, were instead classified as dwarf planets. Planetary geologists still often ignore this definition and consider Ceres to be a planet anyway. Ceres is a dwarf planet, but there is some confusion about whether it is also an asteroid. A NASA webpage states that Vesta, the belt's second largest object, is the largest asteroid. The IAU has been equivocal on the subject, though its minor planet center, the organization charged with cataloging such objects, notes that dwarf planets may have dual designations, and the joint IAU/USGS/NASA Gazetteer categorizes Ceres as both asteroid and a dwarf planet. Ceres follows an orbit between Mars and Jupiter, near the middle of the asteroid belt, with an orbital period, year, of 4.6 Earth years. Compared to other planets and dwarf planets, Ceres's orbit is moderately tilted relative to that of Earth. Its inclination, I, is 10.6 degrees, compared to 7 degrees for Mercury and 17 degrees for Pluto. It is also slightly elongated, with an eccentricity, E, equals 0.08, compared to 0.09 for Mars. Ceres is not part of an asteroid family, probably due to its large proportion of ice, as smaller bodies with the same composition would have sublimated to nothing over the age of the solar system. It was once thought to be a member of the Gophian family, the members of which share similar proper orbital elements, suggesting a common origin through an asteroid collision in the past. Ceres was later found to have a different composition from the Gophian family and appears to be an interloper, having similar orbital elements but not a common origin. Due to their small masses and large separations, objects within the asteroid belt rarely fall into gravitational resonances with each other. Nevertheless, Ceres is able to capture other asteroids into temporary 1:1 resonances, making them temporary Trojans, for periods from a few 100,000 to more than 2 million years. 50 such objects have been identified. Ceres is close to a 1:1 mean motion orbital resonance with Pallas. Their proper orbital periods differ by 0.2%, but not close enough to be significant over astronomical timescales. The rotation period of Ceres, the Sirian day, is 9 hours and 4 minutes. The small equatorial crater of Kate is selected as its prime meridian. Ceres has an axial tilt of 4 degrees, small enough for its polar regions to contain permanently shadowed craters that are expected to act as cold traps and accumulate water ice over time, similar to what occurs on the Moon and Mercury. About 0.14% of water molecules released from the surface are expected to end up in the traps, hopping an average of 3 times before escaping or being trapped. Dawn, the first spacecraft to orbit Ceres, determined that the north polar axis points at right ascension 19 hours 25 minutes 40.3 s, 291.418 degrees, declination plus 66 degree 45 feet 50 inches, about 1.5 degrees from Delta Draconis, which means an axial tilt of 4 degrees. This means that Ceres currently sees little to no seasonal variation in sunlight by latitude. Over the course of 3 million years, gravitational influence from Jupiter and Saturn has triggered cyclical shifts in Ceres's axial tilt, ranging from 2 to 20 degrees, meaning that seasonal variation in sun exposure has occurred in the past, with the last period of seasonal activity estimated at 14,000 years ago. Those craters that remain in shadow during periods of maximum axial tilt are the most likely to retain water ice from eruptions or cometary impacts over the age of the Solar System. Ceres is the largest asteroid in the main asteroid belt. It has been classified as a C-type or carbonaceous asteroid and, due to the presence of clay minerals, as a G-type asteroid. It has a similar, but not identical, composition to that of carbonaceous chondrite meteorites. It is an oblate spheroid, with an equatorial diameter 8% larger than its polar diameter. Measurements from the Dawn spacecraft found a mean diameter of 939.4 kilometers, 583.7 miles, and a mass of 9.38 times 1020 kg. This gives Ceres a density of 2.16 g/cm3, suggesting that a quarter of its mass is water ice. Ceres comprises 40% of the estimated 2394 plus or minus 5 times 1018 kg mass of the asteroid belt, and it has 3 plus 12 times the mass of the next asteroid, Vesta, but it is only 1.3% the mass of the Moon. It is close to being in hydrostatic equilibrium, but some deviations from an equilibrium shape have yet to be explained. Assuming it is in equilibrium, Ceres is the only dwarf planet that is always within the orbit of Neptune. 66 modeling has suggested Ceres's rocky material is partially differentiated, and that it may possess a small core, but the data is also consistent with a mantle of hydrated silicates and no core. Because Dawn lacked a magnetometer, it is not known if Ceres has a magnetic field. It is believed not to. Ceres's internal differentiation may be related to its lack of a natural satellite, as satellites of main belt asteroids are mostly believed to form from collisional disruption, creating an undifferentiated, rubble pile structure. The surface composition of Ceres is homogeneous on a global scale, and is rich in carbonates and ammoniated phyllosilicates that have been altered by water, though water ice in the regolith varies from approximately 10% in polar latitudes to much drier, even ice-free. In the equatorial regions, studies using the Hubble Space Telescope show graphite, sulfur, and sulfur dioxide on Ceres's surface. The graphite is evidently the result of space weathering on Ceres's older surfaces. The latter two are volatile under Sirian conditions and would be expected to either escape quickly or settle in cold traps, and so are evidently associated with areas with relatively recent geological activity. Organic compounds were detected in Ernutet crater, and most of the planet's near surface is rich in carbon, at approximately 20% by mass. The carbon content is more than 5 times higher than in carbonaceous chondrite meteorites analyzed on Earth. The surface carbon shows evidence of being mixed with products of rock-water interactions, such as clays. This chemistry suggests Ceres formed in a cold environment, perhaps outside the orbit of Jupiter, and that it accreted from ultracarbon-rich materials in the presence of water, which could provide conditions favorable to organic chemistry. Dawn revealed that Ceres has a heavily cratered surface, though with fewer large craters than expected. Models based on the formation of the current asteroid belt had predicted Ceres should have 10 to 15 craters larger than 400 kilometers, 250 miles, in diameter. The largest confirmed crater on Ceres, Kirwan Basin, is 284 kilometers, 176 miles, across. The most likely reason for this is viscous relaxation of the crust slowly flattening out larger impacts. Ceres's north polar region shows far more cratering than the equatorial region, with the eastern equatorial region in particular comparatively lightly cratered. The overall size frequency of craters of between 20 and 100 kilometers, 1060 mi, is consistent with their having originated in the late heavy bombardment, with craters outside the ancient polar regions likely erased by early cryovolcanism. 3 large shallow basins, planitia, with degraded rims are likely to be eroded craters. The largest, Vendemia planitia, at 800 kilometers, 500 miles, across, is also the largest single geographical feature on Ceres. 2 of the 3 have higher than average ammonium concentrations. Dawn observed 4,423 boulders larger than 105 m, 344 feet, in diameter on the surface of Ceres. These boulders likely formed through impacts, and are found within or near craters, though not all craters contain boulders. Large boulders are more numerous at higher latitudes. Boulders on Ceres are brittle and degrade rapidly due to thermal stress. At dawn and dusk, the surface temperature changes rapidly, and meteoritic impacts. Their maximum age is estimated to be 150 million years, much shorter than the lifetime of boulders on Vesta. Although Ceres lacks plate tectonics, with the vast majority of its surface features linked either to impacts or to cryovolcanic activity, several potentially tectonic features have been tentatively identified on its surface, particularly in its eastern hemisphere. The Samhain-Cattini, kilometer-scale linear fractures on Ceres's surface, lack any apparent link to impacts and bear a stronger resemblance to pit crater chains, which are indicative of buried normal faults. Also, several craters on Ceres have shallow, fractured floors consistent with cryomagmatic intrusion. Ceres has one prominent mountain, Ahana Mons. This appears to be a cryovolcano and has few craters, suggesting a maximum age of 240 million years. Its relatively high gravitational field suggests it is dense, and thus composed more of rock than ice, and that its placement is likely due to diapirism of a slurry of brine and silicate particles from the top of the mantle. It is roughly antipodal to Kirwan Basin. Seismic energy from the Kirwan-forming impact may have focused on the opposite side of Ceres, fracturing the outer layers of the crust and triggering the movement of high-viscosity cryomagma, muddy water ice softened by its content of salts, onto the surface. 88 Kirwan 2 shows evidence of the effects of liquid water due to impact melting of subsurface ice. A 2018 computer simulation suggests that cryovolcanoes on Ceres, once formed, recede due to viscous relaxation over several hundred million years. The team identified 22 features as strong candidates for relaxed cryovolcanoes on Ceres's surface. Yammer Mons, an ancient, impact-cratered peak, resembles Ahana Mons despite being much older, due to it lying in Ceres's northern polar region, where lower temperatures prevent viscous relaxation of the crust. Models suggest that, over the past billion years, one cryovolcano has formed on Ceres on average every 50 million years. The eruptions are not uniformly distributed over Ceres, but may be linked to ancient impact basins. The model suggests that, contrary to findings at Ahana Mons, Cerean cryovolcanoes must be composed of far less dense material than average for Ceres's crust, or the observed viscous relaxation could not occur. An unexpectedly large number of Cerean craters have central pits, perhaps due to cryovolcanic processes. Others have central peaks. Hundreds of bright spots, faculae, have been observed by dawn, the brightest in the middle of 80 kilometers, 50 miles, a crater. The bright spot in the center of a crater is named Ceralia Facula, and the group of bright spots to its east, Venalia Faculae. A crater possesses a pit 9-10 km wide, partially filled by a central dome. The dome postdates the faculae and is likely due to freezing of a subterranean reservoir, comparable to Pingos in Earth's Arctic region. A haze periodically appears above Ceralia, supporting the hypothesis that some sort of outgassing or sublimating ice formed the bright spots. In March 2016, dawn found definitive evidence of water ice on the surface of Ceres at Oxo crater. On December 9, 2015, NASA scientists reported that the bright spots on Ceres may be due to a type of salt from evaporated brine containing magnesium sulfate hexahydrate, MgSO46H2O. The spots were also found to be associated with ammonia-rich clays. Near-infrared spectra of these bright areas were reported in 2017 to be consistent with a large amount of sodium carbonate, Na2CO3, and smaller amounts of ammonium chloride, NH4Cl, or ammonium bicarbonate, NH4HCO3. These materials have been suggested to originate from the crystallization of brines that reached the surface. In August 2020, NASA confirmed that Ceres was a water-rich body with a deep reservoir of brine that percolated to the surface in hundreds of locations, causing bright spots, including those in a crater. The active geology of Ceres is driven by ice and brines. Water leached from rock is estimated to possess a salinity of around 5%. Altogether, Ceres is approximately 50% water by volume, compared to 0.1% for Earth, and 73% rock by mass. Ceres's largest craters are several kilometers deep, inconsistent with an ice-rich shallow subsurface. The fact that the surface has preserved craters almost 300 kilometers, 200 miles, in diameter indicates that the outermost layer of Ceres is roughly 1,000 times stronger than water ice. This is consistent with a mixture of silicates, hydrated salts, and methane clathrates, with no more than 30% water ice by volume. Gravity measurements from dawn have generated three competing models for Ceres's interior. In the three-layer model, Ceres is thought to consist of an outer, 40 kilometers, 25 miles, thick crust of ice, salts, and hydrated minerals, and an inner muddy mantle of hydrated rock, such as clays, separated by a 60 kilometers, 37 miles, layer of a muddy mixture of brine and rock. It is not possible to tell if Ceres's deep interior contains liquid or a core of dense material rich in metal, but the low central density suggests it may retain about 10% porosity. One study estimated the densities of the core and mantle/crust to be 2.46, 2.90 and 1.68, 1.95 g/cm3 respectively, with the mantle and crust together being 7190 km, 4120 m, thick. Only partial dehydration, expulsion of ice, from the core is expected, though the high density of the mantle relative to water ice reflects its enrichment in silicates and salts. That is, the core, if it exists, the mantle and crust all consist of rock and ice, though in different ratios. Ceres's mineral composition can be determined, indirectly, only for its outer 100 kilometers, 60 miles. The solid outer crust, 40 kilometers, 25 miles, thick, is a mixture of ice, salts, and hydrated minerals. Under that is a layer that may contain a small amount of brine. This extends to a depth of at least the 100 kilometers, 60 miles, limit of detection. Under that is thought to be a mantle dominated by hydrated rocks such as clays. In one two-layer model, Ceres consists of a core of chondrules and a mantle of mixed ice and micron-sized solid particulates, mud. Sublimation of ice at the surface would leave a deposit of hydrated particulates perhaps 20 meters thick. The range of the extent of differentiation is consistent with the data, from a large, 360 kilometers, 220 miles, core of 75% chondrules and 25% particulates in a mantle of 75% ice and 25% particulates, to a small, 85 kilometers, 55 miles, core consisting nearly entirely of particulates in a mantle of 30% ice and 70% particulates. With a large core, the core mantle boundary should be warm enough for pockets of brine. With a small core, the mantle should remain liquid below 110 kilometers, 68 miles. In the latter case, a 2% freezing of the liquid reservoir would compress the liquid enough to force some to the surface, producing cryovolcanism. A second two-layer model suggests a partial differentiation of Ceres into a volatile-rich crust and a denser mantle of hydrated silicates. A range of densities for the crust and mantle can be calculated from the types of meteorite thought to have impacted Ceres. With Ci-class meteorites, density 2.46 g/cm3, the crust would be approximately 70 kilometers, 40 miles, thick and have a density of 1.68 g/cm3. With Cm-class meteorites, density 2.9 g/cm3, the crust would be approximately 190 kilometers, 120 miles, thick and have a density of 1.9 g/cm3. Best fit modeling yields a crust approximately 40 kilometers, 25 miles, thick with a density of approximately 1.25 g/cm3, and a mantle/core density of approximately 2.4 g/cm3. In 2017, Dawn confirmed that Ceres has a transient atmosphere of water vapor. Hints of an atmosphere had appeared in early 2014, when the Herschel Space Observatory detected localized mid-latitude sources of water vapor on Ceres, no more than 60 kilometers, 40 miles, in diameter, which each give off approximately 1,026 molecules, 3 kilograms, of water per second. Two potential source regions, designated Piazzi, 123 degrees east, 21 degrees north, and Region A, 231 degrees east, 23 degrees north, were visualized in the near-infrared as dark areas. Region A also has a bright center, by the Keck Observatory. Possible mechanisms for the vapor release are sublimation from approximately 0.6 square kilometers, 0.2 square miles, of exposed surface ice, cryovolcanic eruptions resulting from radiogenic internal heat 109, or pressurization of a subsurface ocean due to thickening of an overlying layer of ice. In 2015, David Jewett included Ceres in his list of active asteroids. Surface water ice is unstable at distances less than 50 from the Sun, so it is expected to sublime if exposed directly to solar radiation. Water ice can migrate from the deep layers of Ceres to the surface, but escapes in a short time. Surface sublimation would be expected to be lower when Ceres is farther from the Sun in its orbit, and internally powered emissions should not be affected by its orbital position. The limited data previously available suggested cometary-style sublimation, but evidence from Dawn suggests geologic activity could be at least partially responsible. Studies using Dawn's gamma-ray and neutron detector, GRAND, reveal that Ceres accelerates electrons from the solar wind. The most accepted hypothesis is that these electrons are being accelerated by collisions between the solar wind and a tenuous water vapor exosphere. Bow shocks like these could also be explained by a transient magnetic field, but this is considered less likely, as the interior of Ceres is not thought to be sufficiently electrically conductive. Ceres is a surviving protoplanet that formed 4.56 billion years ago, alongside Pallas and Vesta, one of only 3 remaining in the inner solar system, with the rest either merging to form terrestrial planets, being shattered in collisions, or being ejected by Jupiter. Despite Ceres's current location, its composition is not consistent with having formed within the asteroid belt. It seems rather that it formed between the orbits of Jupiter and Saturn, and was deflected into the asteroid belt as Jupiter migrated outward. The discovery of ammonium salts in a crater supports an origin in the outer solar system, as ammonia is far more abundant in that region. The early geological evolution of Ceres was dependent on the heat sources available during and after its formation, impact energy from planetesimal accretion and decay of radionuclides, possibly including short-lived extinct radionuclides such as aluminium-26. These may have been sufficient to allow Ceres to differentiate into a rocky core and icy mantle, or even a liquid water ocean, soon after its formation. This ocean should have left an icy layer under the surface as it froze. The fact that Dawn found no evidence of such a layer suggests that Ceres's original crust was at least partially destroyed by later impacts thoroughly mixing the ice with the salts and silicate-rich material of the ancient seafloor and the material beneath. Ceres possesses surprisingly few large craters, suggesting that viscous relaxation and cryovolcanism have erased older geological features. The presence of clays and carbonates requires chemical reactions at temperatures above 50 degrees Celsius, consistent with hydrothermal activity. It has become considerably less geologically active over time, with the surface dominated by impact craters. Nevertheless, evidence from Dawn reveals that internal processes have continued to sculpt Ceres's surface to a significant extent, contrary to predictions that Ceres's small size would have ceased internal geological activity early in its history. Although Ceres is not as actively discussed as a potential home for microbial extraterrestrial life as Mars, Europa, Enceladus, or Titan are, it has the most water of any body in the inner solar system after Earth, and the likely brine pockets under its surface could provide habitats for life. It does not experience tidal heating, like Europa or Enceladus, but it is close enough to the Sun, and contains enough long-lived radioactive isotopes, to preserve liquid water in its subsurface for extended periods. The remote detection of organic compounds and the presence of water mixed with 20% carbon by mass in its near surface could provide conditions favorable to organic chemistry. Of the biochemical elements, Ceres is rich in carbon, hydrogen, oxygen, and nitrogen, but phosphorus has yet to be detected, and sulfur, despite being suggested by Hubble UV observations, was not detected by Dawn. Text you wish spoken here. Ceres is a minor planet. Designation 1. Ceres is a dwarf planet in the asteroid belt between the orbits of Mars and Jupiter. It was the first asteroid discovered, on January 1, 1801, by Giuseppe Piazzi at Palermo Astronomical Observatory in Sicily and announced as a new planet. Ceres was later classified as an asteroid and then a dwarf planet, Eris. Minor planet. Designation 136,199. Eris is the most massive and second largest known dwarf planet in the Solar System. It is a trans-Neptunian object, TNO, in the scattered disk and has a high eccentricity orbit. Eris was discovered in January 2005 by a Palomar Observatory-based team led by Mike Brown and verified later that year. In September 2006, it was named after the Greco-Roman goddess of strife and discord. Eris is the 9th most massive known object orbiting the Sun and the 16th most massive overall in the Solar System, counting moons. It is also the largest known object in the Solar System that has not been visited by a spacecraft. Eris has been measured at 2,326 plus or minus 12 kilometers, 1,445 plus or minus 7 miles, in diameter. Its mass is 0.28% that of the Earth and 27% greater than that of Pluto, although Pluto is slightly larger by volume, both having a surface area that is comparable to the area of Russia or Antarctica. Eris has one large known moon, Dysnomia. In February 2016, Eris's distance from the Sun was 96.30, 14.41 billion km, 8.95 billion mi, more than 3 times that of Neptune or Pluto. With the exception of long-period comets, Eris and Dysnomia were the most distant known natural objects in the Solar System until the discovery of 2018 AG37 and 2018 VG18 in 2018. Because Eris appeared to be larger than Pluto, NASA initially described it as the Solar System's 10th planet. This, along with the prospect of other objects of similar size being discovered in the future, motivated the International Astronomical Union, IAU, to define the term planet for the first time. Under the IAU definition approved on August 24, 2006, Eris, Pluto and Ceres are dwarf planets, reducing the number of known planets in the Solar System to 8, the same as before Pluto's discovery in 1930. Observations of a stellar occultation by Eris in 2010 showed that it was slightly smaller than Pluto, which was measured by New Horizons as having a mean diameter of 2,377 plus or minus 4 kilometers, 1,477 plus or minus 2 miles, in July 2015. Eris is a trans-Neptunian dwarf planet, Plutoid. Its orbital characteristics more specifically categorize it as a scattered disk object, SDO, or a TNO that has been scattered from the Kuiper belt into more distant and unusual orbits following gravitational interactions with Neptune as the solar system was forming. Although its high orbital inclination is unusual among the known SDOs, theoretical models suggest that objects that were originally near the inner edge of the Kuiper belt were scattered into orbits with higher inclinations than objects from the outer belt. Because Eris was initially thought to be larger than Pluto, it was described as the 10th planet by NASA and in media reports of its discovery. In response to the uncertainty over its status, and because of ongoing debate over whether Pluto should be classified as a planet, the IAU delegated a group of astronomers to develop a sufficiently precise definition of the term planet to decide the issue. This was announced as the IAU's definition of a planet in the Solar System, adopted on August 24, 2006. At this time, both Eris and Pluto were classified as dwarf planets, a category distinct from the new definition of planet. Brown has since stated his approval of this classification. The IAU subsequently added Eris to its minor planet catalog, designating it 136,199, Eris. Eris has an orbital period of 559 years. Its maximum possible distance from the Sun, aphelion, is 97.50, and its closest, perihelion, is 38.0. As the time of perihelion is defined at the epoch chosen using an unperturbed two-body solution, the further the epoch is from the date of perihelion, the less accurate the result. Numerical integration is required to predict the time of perihelion accurately. Numerical integration by JPL Horizons shows that Eris came to perihelion around 1699 to aphelion around 1977, and will return to perihelion around December 2257. Unlike those of the 8 planets, whose orbits all lie roughly in the same plane as the Earth's, Eris's orbit is highly inclined. It is tilted at an angle of about 44 degrees to the ecliptic. When discovered, Eris and its moon were the most distant known objects in the Solar System, apart from long-period comets and space probes. It retained this distinction until the discovery of 2018 VG18 in 2018. As of 2008, there were approximately 40 known TNOs, most notably 2006 SQ372, 2000-0067, and Sedna, that are currently closer to the Sun than Eris, even although their semi-major axis is larger than that of Eris, 67.80. The Iridian orbit is highly eccentric, and brings Eris to within 37.90 of the Sun, a typical perihelion for scattered objects. This is within the orbit of Pluto, but still safe from direct interaction with Neptune, 37.0. Pluto, on the other hand, like other Plutinos, follows a less inclined and less eccentric orbit and, protected by orbital resonance, can cross Neptune's orbit 62 in about 800 years. Eris will be closer to the Sun than Pluto for some time, see the graph at the left. As of 2007, Eris has an apparent magnitude of 18.7, making it bright enough to be detectable to some amateur telescopes. 63A 200mm, 7.9 in, telescope with a CCD can detect Eris under favorable conditions. The reason it had not been noticed until now is its steep orbital inclination. Searches for large outer solar system objects tend to concentrate on the ecliptic plane, where most bodies are found. Because of the high inclination of its orbit, Eris passes through only a few constellations of the traditional zodiac. It is now in the constellation Ceres. It was in Sculptor from 1876 until 1929 and Phoenix from roughly 1840 until 1875. In 2036 it will enter Pisces and stay there until 2065, when it will enter Aries. It will then move into the northern sky, entering Perseus in 2128 and Camelopardalis, where it will reach its northernmost declination, in 2173. In November 2010, Eris was the subject of one of the most distant stellar occultations yet from Earth. Preliminary data from this event cast doubt on previous size estimates. The teams announced their final results from the occultation in October 2011, with an estimated diameter of 2326 plus or minus 12 km. This makes Eris a little smaller than Pluto by area and diameter, which is 2372 plus or minus 4 km across, although Eris is more massive. It also indicates a geometric albedo of 0.96. It is speculated that the high albedo is due to the surface ices being replenished because of temperature fluctuations as Eris's eccentric orbit takes it closer and farther from the Sunday. The mass of Eris can be calculated with much greater precision. Based on the accepted value for dysnomia's period at the time 15.774 days, Eris is 27% more massive than Pluto. Using the 2011 occultation results, Eris has a density of 2.52 plus or minus 0.07 g/cm3, substantially denser than Pluto, and thus must be composed largely of rocky materials. Models of internal heating via radioactive decay suggest that Eris could have an subsurface ocean of liquid water at the mantle core boundary. Tidal heating of Eris by its moon dysnomia may additionally contribute to the preservation of its possible subsurface ocean. In July 2015, after nearly a decade of Eris being thought to be the 9th largest known object to directly orbit the Sun, close-up imagery from the New Horizons mission determined the volume of Pluto to be slightly larger than that of Eris. Eris is now understood to be the 10th largest known object to directly orbit the Sun by volume, but remains the 9th largest by mass. The Discovery team followed up their initial identification of Eris with spectroscopic observations made at the 8M Gemini North Telescope in Hawaii on January 25, 2005. Infrared light from the object revealed the presence of methane ice, indicating that the surface may be similar to that of Pluto, which at the time was the only TNO known to have surface methane, and of Neptune's moon Triton, which also has methane on its surface. In 2022, near-infrared spectroscopy of Eris by the James Webb Space Telescope, JWST, revealed the presence of deuterated methane ice on its surface, at abundances lower than those in Jupiter family comets like 67P/Churyumov-Gerasimenko. Eris's comparatively low deuterium abundance suggests that its methane is not primordial and instead may have been produced from subsurface geochemical processes. Substantial quantities of nitrogen ice on Eris was also detected by the JWST, and it is presumed to have originated from subsurface processes similar to Eris's likely non-primordial methane. The abundance of nitrogen ice on Eris is estimated to be 1/3 of that of methane by volume. Unlike the somewhat reddish and variegated surfaces of Pluto and Triton, the surface of Eris appears almost white and uniform. Pluto's reddish color is thought to be due to deposits of tholins on its surface, and where these deposits darken the surface, the lower albedo leads to higher temperatures and the evaporation of methane deposits. In contrast, Eris is far enough from the Sun that methane can condense onto its surface even where the albedo is low. The condensation of methane uniformly over the surface reduces any albedo contrasts and would cover up any deposits of red tholins. This methane sublimation and condensation cycle could produce bladed terrain on Eris, similar to those on Pluto. Alternatively, Eris's surface could be refreshed through radiogenic convection of a global methane and nitrogen ice glacier, similar to Pluto's Sputnik Planitia. Spectroscopic observations by the JWST support the idea that Eris's surface is continually refreshing, as no signs of ethane, a byproduct of radiolyzed methane, were detected on Eris's surface. Due to the distant and eccentric orbit of Eris, its surface temperature is estimated to vary from about 30 to 56 K, 243.2 to 217.2 degrees C, 405.7 to 358.9 degree F. Even though Eris can be up to 3 times farther from the Sun than Pluto, it approaches close enough that some of the ices on the surface might warm enough to sublime to form an atmosphere. Because methane and nitrogen are both highly volatile, their presence shows either that Eris has always resided in the distant reaches of the solar system, where it is cold enough for methane and nitrogen ice to persist, or that the celestial body has an internal source to replenish gas that escapes from its atmosphere. This contrasts with observations of another discovered TNO, Haumea, which reveal the presence of water ice but not methane. Eris displays very little variation in brightness as it rotates due to its uniform surface, making measurement of its rotation period difficult. Precise long-term monitoring of Eris's brightness indicates that it is tidally locked to its moon dysnomia, with the rotation period synchronous with the moon's orbital period of 15.78 Earth days. Dysnomia is also tidally locked to Eris, which makes the Eris dysnomia system the second known case of double synchronous rotation, after Pluto and Charon. Previous measurements of Eris's rotation period obtained highly uncertain values ranging tens of hours to several days due to insufficient long-term coverage of Eris's rotation. The axial tilt of Eris has not been measured, but it can be reasonably assumed that it is the same as dysnomia's orbital inclination, which would be about 78 degrees with respect to the ecliptic. If this were the case, most of Eris's northern hemisphere would be illuminated by sunlight, with 30% of the hemisphere experiencing constant illumination in 2018. In 2005, the adaptive optics team at the Keck telescopes in Hawaii carried out observations of the four brightest TNOs, Pluto, Makemake, Haumea, and Eris, using the newly commissioned Laser Guide Star Adaptive Optics System. Images taken on September 10 revealed a moon in orbit around Eris. In keeping with the Xena nickname already in use for Eris, Brown's team nicknamed the moon Gabrielle, after the television warrior princess's sidekick. When Eris received its official name from the IAU, the moon received the name Dysnomia, after the Greek goddess of lawlessness who was Eris's daughter. Brown says he picked it for similarity to his wife's name, Diane. The name also retains an oblique reference to Eris's old informal name Xena, portrayed on television by Lucy Lawless, though the connection was unintentional. Eris, minor planet designation 136,199. Eris, is the most massive and second largest known dwarf planet in the Solar System. It is a trans-Neptunian object, TNO, in the scattered disk and has a high eccentricity orbit. Eris was discovered in January. The Moon is Earth's only natural satellite. It orbits around Earth at an average distance of 384,400 kilometers, 238,900 miles, or about 30 times Earth's diameter, having a sidereal period of 27.3 days and a synodic period of 29.5 days. The Moon faces Earth always with its near side by having a rotation period that equals its orbital period, resulting from being tidally locked to Earth. Its gravitational influence is the main driver of Earth's tides and causes Earth's day to lengthen very slowly. Its diameter is 3,474 kilometers, 2,159 miles, which is roughly 1/4 that of Earth or twice the width of Australia, making it by far the largest and most massive satellite in the Solar System in relation to its parent planet and the fifth largest Solar System satellite overall. The Moon is a satellite planet in geophysical terms and among all planetary mass objects of the Solar System larger and more massive than all known solar dwarf planets. The Moon's mass, density, and surface gravity of about 1/6 of Earth's, at 0.1654 grams, are rivaled among Solar System satellites only by Jupiter's moon Io. The body of the Moon is differentiated and terrestrial, with no significant atmosphere, hydrosphere, or magnetic field. The most widely accepted origin explanation posits that the Moon formed 4.51 billion years ago, not long after Earth's formation, out of the debris from a giant impact between Earth and a hypothesized Mars-sized body called Gaia. It receded to a wider orbit because of tidal interaction with the Earth. The near side of the Moon is marked by dark volcanic maria, seas, which fill the spaces between bright ancient crustal highlands and prominent impact craters. Most of the large impact basins and mare surfaces were in place by the end of the Imbrian period, some 3 billion years ago. The Moon is the brightest celestial object in Earth's night sky. This is mainly due to its large angular diameter, while the reflectance of the lunar surface is comparable to that of asphalt. The apparent size is nearly the same as that of the Sun, allowing it to cover the Sun almost completely during a total solar eclipse. The Moon is, beside when passing through Earth's shadow during a lunar eclipse, always illuminated by the Sun, but from Earth the visible illumination shifts in the course of its orbit, producing the lunar phases. From Earth about 59% of the lunar surface is visible over time due to cyclical shifts in perspective, libration, making parts of the far side of the Moon visible. For Earth and life on it, the Moon has been beside the Sun the most influential celestial object. Throughout human history, the Moon's prominence in Earth's night sky and its consistent cycle of phases have offered a rich source of inspiration and knowledge, for areas from mythology, cosmography, religion, art, and language, to calendar systems, natural science, and spaceflight. The first time an artificial object reached the Moon was September 14, 1959, when the Soviet Union's Luna 2 performed an impact, while the first soft landing was achieved in 1966 by Luna 9. In 1969, humans for the first time arrived on the Moon, landing on July 16 at Mare Tranquillitatis with the lander Eagle of Apollo 11 as part of the United States Apollo program. Until 1972, 5 more crews were sent, with each time 2 men staying for up to 12 days. These missions remain the only times humans have visited an extraterrestrial body. Continued exploration of the Moon has allowed a detailed understanding of the Moon and its significance for Earth and life on it. Isotope dating of lunar samples suggests the Moon formed around 50 million years after the origin of the Solar System. Historically, several formation mechanisms have been proposed, but none satisfactorily explains the features of the Earth-Moon system. A fission of the Moon from Earth's crust through centrifugal force would require too great an initial rotation rate of Earth. Gravitational capture of a preformed Moon depends on an unfeasibly extended atmosphere of Earth to dissipate the energy of the passing Moon. ACO formation of Earth and the Moon together in the primordial accretion disk does not explain the depletion of metals in the Moon. None of these hypotheses can account for the high angular momentum of the Earth-Moon system. The prevailing theory is that the Earth-Moon system formed after a giant impact of a Mars-sized body, named Gaia, with the proto-Earth. The impact blasted material into orbit about the Earth, and the material accreted and formed the Moon just beyond the Earth's Roche limit of 2.56 R. Giant impacts are thought to have been common in the early solar system. Computer simulations of giant impacts have produced results that are consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system. These simulations show that most of the Moon derived from the impactor, rather than the proto-Earth. However, more recent simulations suggest a larger fraction of the Moon derived from the proto-Earth. Other bodies of the inner solar system such as Mars and Vesta have, according to meteorites from them, very different oxygen and tungsten isotopic compositions compared to Earth. However, Earth and the Moon have nearly identical isotopic compositions. The isotopic equalization of the Earth-Moon system might be explained by the post-impact mixing of the vaporized material that formed the two, although this is debated. The impact would have released enough energy to liquefy both the ejecta and the Earth's crust, forming a magma ocean. The liquefied ejecta could have then reaccreted into the Earth-Moon system. Similarly, the newly formed Moon would have had its own lunar magma ocean. Its depth is estimated from about 500 kilometers, 300 miles, to 1,737 kilometers, 1,079 miles. While the giant impact theory explains many lines of evidence, some questions are still unresolved, most of which involve the Moon's composition. 56 example needed above a high-resolution threshold for simulations. A study published in 2022 finds that giant impacts can immediately place a satellite with similar mass and iron content to the Moon into orbit far outside Earth's Roche limit. Even satellites that initially pass within the Roche limit can reliably and predictably survive, by being partially stripped and then torqued onto wider, stable orbits. Artists' depiction of the Moon as it might have appeared in Earth's sky after the late heavy bombardment around 4 billion years ago, when its orbit was half as close to Earth and it appeared 2.8 times larger than today. After the Moon's formation, it settled into a much closer Earth orbit than it has today. Each body therefore appeared much larger in the sky of the other, eclipses were more frequent, and tidal effects were stronger. Due to tidal acceleration, the Moon's orbit around Earth has become significantly larger, with a longer period. Since cooling and stripped of most of its atmosphere, both originating from its initial formation, the lunar surface has been shaped by large impact events and many small ones, forming a landscape featuring craters of all ages. The prominent lunar maria were produced by volcanic activity. Volcanically active until 1.2 billion years ago, most of the Moon's mare basalts erupted during the Imbrian period, 3.3–3.7 billion years ago, though some are as young as 1.2 billion years and some as old as 4.2 billion years. There are differing explanations for the causes behind the eruption of mare basalts, particularly their uneven occurrence, mainly on the near side. Causes of the distribution of the lunar highlands on the far side are also not well understood. One explanation suggests that large meteorites were hitting the Moon in its early history, leaving large craters which then were filled with lava. Other explanations suggest processes of lunar volcanism. The Moon is a very slightly scalene ellipsoid due to tidal stretching, with its long axis displaced 30 degrees from facing the Earth, due to gravitational anomalies from impact basins. Its shape is more elongated than current tidal forces can account for. This fossil bulge indicates that the Moon solidified when it orbited at half its current distance to the Earth, and that it is now too cold for its shape to adjust to its orbit. Size comparison of the main moons of the Solar System with Earth to scale. 19 moons are large enough to be round, several having subsurface oceans and one, Titan, having a considerable atmosphere. The Moon is by size and mass the fifth largest natural satellite of the Solar System, categorizable as one of its planetary mass moons, making it a satellite planet under the geophysical definitions of the term. It is smaller than Mercury and considerably larger than the largest dwarf planet of the Solar System, Pluto. While the minor planet Moon Charon of the Pluto-Charon system is larger relative to Pluto, the Moon is the largest natural satellite of the Solar System relative to their primary planets. The Moon's diameter is about 3,500 kilometers, more than a quarter of Earth's, with the face of the Moon comparable to the width of Australia. The whole surface area of the Moon is about 38 million square kilometers, between the size of the Americas, North and South America, and Africa. The Moon's mass is 1/81st of Earth's, being the second densest among the planetary moons, and having the second highest surface gravity after Io at 0.1654 grams and an escape velocity of 2.38 km per second, 8,600 km per hour, 5,300 miles per hour. Moon's internal structure: solid inner core, iron metallic, molten outer core, hardened mantle, and crust. The crust on the Moon's near side permanently facing Earth is thinner, featuring larger areas flooded by material of the once molten mantle forming today's lunar mare. The Moon is a differentiated body that was initially in hydrostatic equilibrium but has since departed from this condition. It has a geochemically distinct crust, mantle, and core. The Moon has a solid iron-rich inner core with a radius possibly as small as 240 kilometers, 150 miles, and a fluid outer core primarily made of liquid iron with a radius of roughly 300 kilometers, 190 miles. Around the core is a partially molten boundary layer with a radius of about 500 kilometers, 310 miles. This structure is thought to have developed through the fractional crystallization of a global magma ocean shortly after the Moon's formation 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine, clinopyroxene, and orthopyroxene. After about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust atop. The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements. Consistent with this perspective, geochemical mapping made from orbit suggests a crust of mostly anorthosite. The Moon rock samples of the flood lavas that erupted onto the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth. The crust is on average about 50 kilometers, 31 miles, thick. The Moon is the second densest satellite in the Solar System, after Io. However, the inner core of the Moon is small, with a radius of about 350 kilometers, 220 miles, or less, around 20% of the radius of the Moon. Its composition is not well understood, but is probably metallic iron alloyed with a small amount of sulfur and nickel. Analyses of the Moon's time-variable rotation suggest that it is at least partly molten. The pressure at the lunar core is estimated to be 5 GPa, 49,000 atm. An astronaut jumping on the Moon, illustrating that the gravitational pull of the Moon is approximately 1/6 of Earth's. On average, the Moon's surface gravity is 1.62 m/s24, 0.1654 grams, 5.318 feet/s2, about half of the surface gravity of Mars and about 1/6 of Earth's. The Moon's gravitational field is not uniform. The details of the gravitational field have been measured through tracking the Doppler shift of radio signals emitted by orbiting spacecraft. The main lunar gravity features are mascons, large positive gravitational anomalies associated with some of the giant impact basins, partly caused by the dense mare basaltic lava flows that fill those basins. The anomalies greatly influence the orbit of spacecraft about the Moon. There are some puzzles. Lava flows by themselves cannot explain all of the gravitational signature, and some mascons exist that are not linked to mare volcanism. The Moon has an external magnetic field of less than 0.2 nanoteslas, or less than 100,000th that of Earth. The Moon does not currently have a global dipolar magnetic field and only has crustal magnetization likely acquired early in its history when a dynamo was still operating. However, early in its history, 4 billion years ago, its magnetic field strength was likely close to that of Earth today. This early dynamo field apparently expired by about 1 billion years ago, after the lunar core had completely crystallized. Theoretically, some of the remnant magnetization may originate from transient magnetic fields generated during large impacts through the expansion of plasma clouds. These clouds are generated during large impacts in an ambient magnetic field. This is supported by the location of the largest crustal magnetizations situated near the antipodes of the giant impact basins. The thin lunar atmosphere is visible on the Moon's surface at sunrise and sunset with the lunar horizon glow and lunar twilight rays, like Earth's crepuscular rays. This Apollo 17 sketch depicts the glow and rays among the general zodiacal light. The Moon has an atmosphere so tenuous as to be nearly vacuum, with a total mass of less than 10 tons, 9.8 long tons, 11 short tons. The surface pressure of this small mass is around 3 times 1015 atm, 0.3 npa. It varies with the lunar day. Its sources include outgassing and sputtering, a product of the bombardment of lunar soil by solar wind ions. Elements that have been detected include sodium and potassium, produced by sputtering, also found in the atmospheres of Mercury and Io, helium-4 and neon from the solar wind, and argon-40, radon-222, and polonium-210, outgassed after their creation by radioactive decay within the crust and mantle. The absence of such neutral species, atoms or molecules, as oxygen, nitrogen, carbon, hydrogen, and magnesium, which are present in the regolith, is not understood. Water vapor has been detected by Chandrayaan-1 and found to vary with latitude, with a maximum at 60-70 degrees. It is possibly generated from the sublimation of water ice in the regolith. These gases either return into the regolith because of the Moon's gravity or are lost to space, either through solar radiation pressure or, if they are ionized, by being swept away by the solar wind's magnetic field. Studies of Moon magma samples retrieved by the Apollo missions demonstrate that the Moon had once possessed a relatively thick atmosphere for a period of 70 million years between 3 and 4 billion years ago. This atmosphere, sourced from gases ejected from lunar volcanic eruptions, was twice the thickness of that of present-day Mars. The ancient lunar atmosphere was eventually stripped away by solar winds and dissipated into space. A permanent moon dust cloud exists around the Moon, generated by small particles from comets. Estimates are 5 tons of comet particles strike the Moon's surface every 24 hours, resulting in the ejection of dust particles. The dust stays above the Moon approximately 10 minutes, taking 5 minutes to rise, and 5 minutes to fall. On average, 120 kilograms of dust are present above the Moon, rising up to 100 kilometers above the surface. Dust counts made by Leidy's Lunar Dust Experiment, LDEX, found particle counts peaked during the Geminid, Quadrantid, Northern Taurid, and Omicron Centaurid meteor showers, when the Earth and Moon pass through comet debris. The lunar dust cloud is asymmetric, being more dense near the boundary between the Moon's dayside and nightside. Gene Cernan with lunar dust stuck on his suit. Lunar dust is highly abrasive and can cause damage to human lungs, nervous, and cardiovascular systems. Ionizing radiation from cosmic rays, the Sun, and the resulting neutron radiation produce radiation levels on average of 1.369 millisieverts per day during lunar daytime, which is about 2.6 times more than on the International Space Station with 0.53 millisieverts per day at about 400 kilometers above Earth in orbit, 5 to 10 times more than during a transatlantic flight, 200 times more than on Earth's surface. For further comparison, radiation on a flight to Mars is about 1.84 millisieverts per day and on Mars on average 0.64 millisieverts per day, with some locations on Mars possibly having levels as low as 0.342 millisieverts per day. The Moon's axial tilt with respect to the ecliptic is only 1.5427 degrees, much less than the 23.44 degrees of Earth. Because of this small tilt, the Moon's solar illumination varies much less with season than on Earth, and it allows for the existence of some peaks of eternal light at the Moon's north pole, at the rim of the crater Peary. The surface is exposed to drastic temperature differences ranging from 140 degrees Celsius to 171 degrees C depending on the solar irradiance. Because of the lack of atmosphere, temperatures of different areas vary particularly upon whether they are in sunlight or shadow, making topographical details play a decisive role on local surface temperatures. Parts of many craters, particularly the bottoms of many polar craters, are permanently shadowed. These craters of eternal darkness have extremely low temperatures. The Lunar Reconnaissance Orbiter measured the lowest summer temperatures in craters at the southern pole at 35 K, 238 degrees C, 397 degree F, and just 26 K, 247 degrees C, 413 degree F, close to the winter solstice in the North Polar crater Hermite. This is the coldest temperature in the solar system ever measured by a spacecraft, colder even than the surface of Pluto. Blanketed on top of the Moon's crust is a highly comminuted, broken into ever smaller particles, an impact-gardened mostly gray surface layer called regolith, formed by impact processes. The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow and a scent resembling spent gunpowder. The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from 10-15 m, 33-49 feet, in the highlands and 4-5 m, 13-16 feet, in the Maria. Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock many kilometers thick. These extreme conditions, for example, are considered to make it unlikely for spacecraft to harbor bacterial spores at the Moon longer than just one lunar orbit. The topography of the Moon has been measured with laser altimetry and stereo image analysis. Its most extensive topographic feature is the giant farside South Pole Aitken Basin, some 2,240 kilometers, 1,390 miles, in diameter, the largest crater on the Moon and the second largest confirmed impact crater in the Solar System. At 13 kilometers, 8.1 miles, deep, its floor is the lowest point on the surface of the Moon. The highest elevations of the Moon's surface are located directly to the northeast, which might have been thickened by the oblique formation impact of the South Pole Aitken Basin. Other large impact basins such as Imbrium, Serenitatis, Chrysium, Smithii, and Oriental possess regionally low elevations and elevated rims. The far side of the lunar surface is on average about 1.9 kilometers, 1.2 miles, higher than that of the near side. The discovery of fault scarp cliffs suggests that the Moon has shrunk by about 90 meters, 300 feet, within the past billion years. Similar shrinkage features exist on Mercury. Mare Frigoris, a basin near the North Pole long assumed to be geologically dead, has cracked and shifted. Since the Moon does not have tectonic plates, its tectonic activity is slow and cracks develop as it loses heat. The names of the main volcanic features, the Maria, blue, and some crater, brown, features of the near side of the Moon. The main features visible from Earth by the naked eye are dark and relatively featureless lunar plains called Maria, singular mare, Latin for seas, as they were once believed to be filled with water, are vast solidified pools of ancient basaltic lava. Although similar to terrestrial basalts, lunar basalts have more iron and no minerals altered by water. The majority of these lava deposits erupted or flowed into the depressions associated with impact basins. Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side Maria. Almost all Maria are on the near side of the Moon, and cover 31% of the surface of the near side compared with 2% of the far side. This is likely due to a concentration of heat-producing elements under the crust on the near side, which would have caused the underlying mantle to heat up, partially melt, rise to the surface and erupt. Most of the Moon's mare basalts erupted during the Imbrian period, 3.3–3.7 billion years ago, though some being as young as 1.2 billion years and as old as 4.2 billion years. Old hardened lava flows of mare Imbrium forming wrinkle ridges in 2006, a study of Ina, a tiny depression in Lacus Felicitatis, found jagged, relatively dust-free features that, because of the lack of erosion by infalling debris, appeared to be only 2 million years old. Moonquakes and releases of gas indicate continued lunar activity. Evidence of recent lunar volcanism has been identified at 70 irregular mare patches, some less than 50 million years old. This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side where the deep crust is substantially warmer because of the greater concentration of radioactive elements. Evidence has been found for 10 million years old basaltic volcanism within the crater Lowell, inside the Oriental Basin. Some combination of an initially hotter mantle and local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities on the far side in the Oriental Basin. The lighter-colored regions of the Moon are called terrae, or more commonly highlands, because they are higher than most Maria. They have been radiometrically dated to having formed 4.4 billion years ago, and may represent plagioclase cumulates of the lunar magma ocean. In contrast to Earth, no major lunar mountains are believed to have formed as a result of tectonic events. The concentration of Maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow-velocity impact of a second moon of Earth a few tens of millions of years after the Moon's formation. Alternatively, it may be a consequence of asymmetrical tidal heating when the Moon was much closer to the Earth. A gray, many-ridged surface from high above. The largest feature is a circular ringed structure with high-walled sides and a lower central peak. The entire surface out to the horizon is filled with similar structures that are smaller and overlapping. A major geologic process that has affected the Moon's surface is impact cratering, with craters formed when asteroids and comets collide with the lunar surface. There are estimated to be roughly 300,000 craters wider than 1 kilometer, 0.6 miles, on the Moon's near side. The lunar geologic timescale is based on the most prominent impact events, including Eris, Imbrium, and Oriental, structures characterized by multiple rings of uplifted material, between hundreds and thousands of kilometers in diameter and associated with a broad apron of ejecta deposits that form a regional stratigraphic horizon. The lack of an atmosphere, weather, and recent geological processes mean that many of these craters are well preserved. Although only a few multi-ring basins have been definitively dated, they are useful for assigning relative ages. Because impact craters accumulate at a nearly constant rate, counting the number of craters per unit area can be used to estimate the age of the surface. The radiometric ages of impact melted rocks collected during the Apollo missions cluster between 3.8 and 4.1 billion years old. This has been used to propose a late heavy bombardment period of increased impacts. Lunar swirls are enigmatic features found across the Moon's surface. They are characterized by a high albedo, appear optically immature, i.e. the optical characteristics of a relatively young regolith, and often have a sinuous shape. Their shape is often accentuated by low albedo regions that wind between the bright swirls. They are located in places with enhanced surface magnetic fields, and many are located at the antipodal point of major impacts. Well-known swirls include the Reiner Gamma feature and Marangini. They are hypothesized to be areas that have been partially shielded from the solar wind, resulting in slower space. Liquid water cannot persist on the lunar surface. When exposed to solar radiation, water quickly decomposes through a process known as photodissociation and is lost to space. However, since the 1960s, scientists have hypothesized that water ice may be deposited by impacting comets or possibly produced by the reaction of oxygen-rich lunar rocks, and hydrogen from solar wind, leaving traces of water which could possibly persist in cold, permanently shadowed craters at either pole on the Moon. Computer simulations suggest that up to 14,000 square kilometers, 5,400 square miles, of the surface may be in permanent shadow. The presence of usable quantities of water on the Moon is an important factor in rendering lunar habitation as a cost-effective plan. The alternative of transporting water from Earth would be prohibitively expensive. In years since, signatures of water have been found to exist on the lunar surface. In 1994, the BIST-ATIC radar experiment located on the Clementine spacecraft indicated the existence of small, frozen pockets of water close to the surface. However, later radar observations by Arecibo suggest these findings may rather be rocks ejected from young impact craters. In 1998, the neutron spectrometer on the Lunar Prospector spacecraft showed that high concentrations of hydrogen are present in the first meter of depth in the regolith near the polar regions. Volcanic lava beads, brought back to Earth aboard Apollo 15, showed small amounts of water in their interior. In 2008, NASA's Moon Mineralogy Mapper equipment on India's Chandrayaan-1 discovered, for the first time, water-rich minerals, shown in blue around a small crater from which they were ejected. The 2008 Chandrayaan-1 spacecraft has since confirmed the existence of surface water ice, using the onboard Moon Mineralogy Mapper. The spectrometer observed absorption lines common to hydroxyl, in reflected sunlight, providing evidence of large quantities of water ice, on the lunar surface. The spacecraft showed that concentrations may possibly be as high as 1000 ppm. Using the mapper's reflectance spectra, indirect lighting of areas in shadow confirmed water ice within 20 degrees latitude of both poles in 2018. In 2009, LaCrosse sent a 2,300 kilograms, 5,100 pounds, impactor into a permanently shadowed polar crater, and detected at least 100 kilograms, 220 pounds, of water in a plume of ejected material. Another examination of the LaCrosse data showed the amount of detected water to be closer to 155 plus or minus 12 kilograms, 342 plus or minus 26 pounds. In May 2011, 615-1410 ppm water in melt inclusions in lunar sample 74,220 was reported, the famous high titanium orange glass soil of volcanic origin collected during the Apollo 17 mission in 1972. The inclusions were formed during explosive eruptions on the Moon approximately 3.7 billion years ago. This concentration is comparable with that of magma in Earth's upper mantle. Although of considerable selenological interest, this insight does not mean that water is easily available since the sample originated many kilometers below the surface, and the inclusions are so difficult to access that it took 39 years to find them with a state-of-the-art ion microprobe instrument. Analysis of the findings of the Moon Mineralogy Mapper, M3, revealed in August 2018 for the first time definitive evidence for water ice on the lunar surface. The data revealed the distinct reflective signatures of water ice, as opposed to dust and other reflective substances. 156 The ice deposits were found on the north and south poles, although it is more abundant in the south, where water is trapped in permanently shadowed craters and crevices, allowing it to persist as ice on the surface since they are shielded from the sun. In October 2020, astronomers reported detecting molecular water on the sunlit surface of the Moon by several independent spacecraft, including the Stratospheric Observatory for Infrared Astronomy, SOFIA. The Earth and the Moon form the Earth-Moon satellite system with a shared center of mass, or barycenter. This barycenter is 1,700 kilometers, 1,100 miles, about a quarter of Earth's radius, beneath the Earth's surface. The Moon's orbit is slightly elliptical, with an orbital eccentricity of 0.055. The semi-major axis of the geocentric lunar orbit, called the lunar distance, is approximately 400,000 kilometers, 250,000 miles or 1.28 light seconds. The Moon makes a complete orbit around Earth with respect to the fixed stars, its sidereal period, about once every 27.3 days. However, because the Earth-Moon system moves at the same time in its orbit around the Sun, it takes slightly longer, 29.5 days, to return at the same lunar phase, completing a full cycle, as seen from Earth. This synodic period or synodic month is commonly known as the lunar month and is equal to the length of the solar day on the Moon. Due to tidal locking, the Moon has a 1:1 spin-orbit resonance. This rotation-orbit ratio makes the Moon's orbital periods around Earth equal to its corresponding rotation periods. This is the reason for only one side of the Moon, its so-called near side, being visible from Earth. That said, while the movement of the Moon is in resonance, it still is not without nuances such as libration, resulting in slightly changing perspectives, making over time and location on Earth about 59% of the Moon's surface visible from Earth. Unlike most satellites of other planets, the Moon's orbital plane is closer to the ecliptic plane than to the planet's equatorial plane. The Moon's orbit is subtly perturbed by the Sun and Earth in many small, complex, and interacting ways. For example, the plane of the Moon's orbit gradually rotates once every 18.61 years 163, which affects other aspects of lunar motion. These follow-on effects are mathematically described by Cassini's laws. Minimum, mean and maximum distances of the Moon from Earth with its angular diameter as seen from Earth's surface, to scale the gravitational attraction that Earth and the Moon, as well as the Sun, exert on each other manifests in a slightly greater attraction on the sides closest to each other, resulting in tidal forces. Ocean tides are the most widely experienced result of this, but tidal forces also considerably affect other mechanics of Earth, as well as the Moon and their system. The lunar solid crust experiences tides of around 10 centimeters, 4 in, amplitude over 27 days, with three components, a fixed one due to Earth, because they are in synchronous rotation, a variable tide due to orbital eccentricity and inclination, and a small varying component from the Sunday. The Earth-induced variable component arises from changing distance and libration, a result of the Moon's orbital eccentricity and inclination. If the Moon's orbit were perfectly circular and uninclined, there would only be solar tides. According to recent research, scientists suggest that the Moon's influence on the Earth may contribute to maintaining Earth's magnetic field. The cumulative effects of stress built up by these tidal forces produces moonquakes. Moonquakes are much less common and weaker than are earthquakes, although moonquakes can last for up to an hour, significantly longer than terrestrial quakes because of scattering of the seismic vibrations in the dry fragmented upper crust. The existence of moonquakes was an unexpected discovery from seismometers placed on the Moon by Apollo astronauts from 1969 through 1972. The most commonly known effect of tidal forces are elevated sea levels called ocean tides. While the Moon EXE. The Moon is Earth's only natural satellite. It orbits around Earth at an average distance of 384,400 kilometers, 238,900 miles, or about 30 times Earth's diameter, having a sidereal period of 27.3 days and a synodic period of 29.5 days. The Moon faces Earth always with its near side by having a rotation period that equals its orbital period, resulting from being tidally locked to Earth. Its gravitational influence is the main driver of Earth's tides and causes Earth's day to lengthen very slowly. Its diameter is 3,474 kilometers, 2,159 miles, which is roughly 1/4 that of Earth or twice the width of Australia, making it by far the largest and most massive satellite in the Solar System in relation to its parent planet and the 5th largest Solar System satellite overall. The Moon is a satellite planet in geophysical terms and among all planetary mass objects of the Solar System larger and more massive than all known solar dwarf planets. The Moon's mass, density, and surface gravity of about 1/6 of Earth's, at 0.1654 grams,